4.24 light-years, 25,278,000,000,000 miles. At the speed of Voyager 1, the fastest object humanity has ever launched into deep space, the journey to Proxima Centauri, our nearest neighbouring star, would take approximately 73,000 years. Not 73,000 days, not 73,000 months, 73,000 years. And that is the problem. Faster than light travel sounds like a promise, a solution. A shortcut through the dark between worlds. But when you run the numbers, the universe starts saying something much colder. The speed of light is not simply a speed limit posted on a cosmic highway. It is a wall written into the geometry of reality itself. And it may be a wall that nothing made of matter, nothing with mass, nothing built by human hands or any other hands in the universe can ever cross. Tonight, we're going to follow faster than light travel from the first equation that allowed it to exist on paper, through the laboratories that are actively testing whether any version of it can exist in physical reality, all the way to the quietest and most uncomfortable possibility of all, that the wall does not just stop us, that it may stop everyone. We will look at why the warp drive is more physically real than most people realize. We will look at what it actually requires to function. We will look at why the universe becomes more hostile the faster you try to move through it, and how that hostility compounds in ways that are not immediately obvious. We will look at what all of this means for the question of whether any intelligence, anywhere in this galaxy, in all of its 13 billion years, has ever managed to cross the distance between stars. And we will look at the one detail, refined by research published in the last several years, that makes the entire question far stranger and more interesting than it first appeared when the relevant mathematics was written down. If this is the kind of mission briefing you want more of, subscribe and stay with the crew. Strap in, we begin. But in recent years, a series of physicists have published work that quietly changes the shape of that question. Not because it solves the energy problem, not because anyone has built a prototype, not because a working warp drive is waiting in a classified laboratory somewhere, because it shows us exactly where the wall is. And in showing us that with more precision than we had before, it has revealed that the wall may be standing in a different location than we assumed for the first 3 decades after the relevant mathematics was first written down. The first thing to understand is distance. Not distance in the familiar sense. Not the distance between cities, or between continents, or even between the Earth and the Moon. We need to talk about a different kind of distance. The kind that has no human reference point. The kind where every analogy you try to construct eventually breaks down, leaving you standing alone with a number that can be written and read but cannot truly be felt. Proxima Centauri is 4.24 light-years away. That sentence is easy to read. 8 words. It passes through the mind the way most large astronomical numbers pass through. Acknowledged, noted, filed somewhere under the heading of very far away, and then effectively forgotten because the mind has no shelf large enough to hold it. Our brains evolved over millions of years to track distances measured in footsteps, in hours of walking, in the span of a river valley or the width of a sea crossing. The cognitive machinery we use to feel distance was calibrated by our ancestors against the scale of a single planet. Asking that same machinery to genuinely feel 4 light-years is like asking an abacus to run a weather simulation. The instrument is not wrong. It is simply not built for this. So let us slow down and actually try. Not simply reading the number, trying to inhabit it. Light travels at 186,000 miles per second. In one single second, a photon of light could travel from New York to Los Angeles and back roughly 37 times. In 8 minutes, it crosses the 93 million miles between the Earth and the Sun, the same journey that every photon of sunlight completes every day before reaching your skin or warming a leaf or filling a room with morning light. In about 1.3 seconds, it crosses the 250,000 miles between the Earth and the Moon, the distance that the Apollo astronauts took 3 days to cross in their spacecraft. And in 1 full year, moving at that speed without deviation, light covers roughly 5.88 trillion miles. That is 1 light year. 5.88 trillion miles. A number so large that if you counted to it at 1 number per second, the count would take approximately 186,000 years. Proxima Centauri is 4.24 of those years away, about 24.9 trillion miles. If you tried to drive there in a car at highway speed, never stopping for fuel or rest, driving continuously at 60 miles per hour from the moment you started, The trip would take about 47 billion years. The universe itself is only about 13.8 billion years old. You would need 3.5 universe lifetimes to complete the drive. The numbers stop being useful at that scale. They become sounds, arrangements of syllables that point at something without conveying it. So try a physical model. Imagine the sun is the size of a grapefruit. A medium grapefruit sitting on a table in front of you. At that scale, the Earth is a grain of sand sitting about 1 meter away from the grapefruit. The Moon is a speck of dust orbiting that grain of sand. Mars is another tiny grain of sand about 1.5 meters away. Jupiter, the largest planet in the solar system, is a marble about 5 meters from the grapefruit. Saturn is another marble, a bit smaller, at nearly 10 meters. The outer planets, Uranus and Neptune, are smaller beads at about 20 and 30 meters. The Oort cloud, the distant shell of frozen comets and rocky bodies that marks the gravitational outer boundary of our solar system, extends roughly 6 kilometers in every direction from your table. 6 kilometers of solar system, centered on a grapefruit. Now, at that same scale, Proxima Centauri, the nearest other star, is approximately 270 kilometers away. 2 grapefruits, 270 kilometers of near-perfect vacuum between them, each surrounded by its own family of planets, each completely unreachable from the other by any means we currently possess. If you are in Chicago, the nearest other star is somewhere around St. Louis. If you are in London, it is out in the North Sea. If you are in Los Angeles, it is somewhere in Nevada. If you are in Tokyo, it is somewhere over the horizon on the Japanese coast. 270 kilometers, and that is our closest neighbor. The second closest star system is Alpha Centauri, a triple star system that includes Proxima at roughly the same distance. The third closest is Barnard's star, at almost twice the distance. The vast majority of the stars visible in the night sky are at distances of hundreds or thousands of light years, putting them, on the grapefruit scale, somewhere between tens of thousands and millions of kilometers away. The Milky Way galaxy contains somewhere between 200 and 400 billion stars. At the grapefruit scale, the galaxy is a disk roughly 6.5 million kilometers across, about 17 times the actual Earth-Moon distance, end to end, just across our own galaxy. And the Milky Way is not particularly large as galaxies go. It is a mid-sized spiral galaxy in a relatively quiet corner of the observable universe. We live inside an ocean that makes every ocean on Earth look like a puddle. Now consider what we have actually sent toward the nearest shore. Voyager 1 launched on September 5th, 1977. It was one of the most precisely engineered spacecraft ever built. A machine roughly the size of a small car, loaded with instruments and cameras and a high-gain antenna, launched on a trajectory calculated with extraordinary care to intercept Jupiter and use its gravitational field to redirect and accelerate the spacecraft towards Saturn, and then to use Saturn's gravitational field to redirect it again, this time out of the solar plane and toward interstellar space. The technique is called a gravity assist, or gravitational slingshot. It works because a spacecraft flying past a massive planet is briefly accelerated by the planet's gravity, and if the geometry is right, the spacecraft can carry that extra velocity away when it departs. Voyager 1 gained significant speed from each encounter. It passed Jupiter in March 1979, Saturn in November 1980. By 1981, it was headed outward on a trajectory that would carry it away from the Sun forever. In 2012, Voyager 1 crossed the heliopause, the boundary where the outward pressure of the solar wind gives way to the ambient pressure of the interstellar medium. After 35 years of travel, it had finally left the solar system, at least by the measure of the boundary between solar influence and interstellar space. It became the first human-made object to enter the actual space between stars. Voyager 1 is currently more than 23 billion miles from Earth, the most distant human artifact that has ever existed. The faint radio signal it transmits home, using a transmitter with about as much power as a refrigerator light bulb, travels at the speed of light, and still takes more than 22 hours to reach the receiving antennas on Earth. When mission controllers receive data from Voyager, they are listening to a transmission that left the spacecraft nearly a full day before it arrived. The spacecraft itself is moving at approximately 38,000 miles per hour. That speed sounds impressive. In ordinary human context, it is impressive. It is faster than any bullet ever fired, faster than any aircraft ever built, faster than anything the human body can experience and survive. It is fast enough to circle the Earth at the equator in about 40 minutes, but at 38,000 miles per hour, Voyager 1 would take approximately 73,000 years to reach Proxima Centauri. Let that number land in full. All of recorded human civilization is approximately 10,000 years old. From the first permanent settlements in Mesopotamia, from the first written language and the first organized agriculture and the first numerical systems, from the invention of the wheel and the plough, from the Bronze Age empires of Egypt and the city-states of Greece and Rome through the medieval period and the Renaissance and the scientific revolution and the industrial revolution, through the invention of the telephone and the airplane and the nuclear bomb and the computer and the internet, all the way to the moment you are listening to this. Every event in recorded human history, every battle and discovery and invention and collapse and rebuilding, every person who has ever been remembered, every work of art or literature or science that has survived, everything we call civilization, fits inside a window of time 7 times smaller than the travel time to our nearest stellar neighbour at the speed of our fastest spacecraft. To reach Proxima Centauri at Voyager's speed, you would need to watch all of recorded human history unfold 7 complete times, from the first cities to whatever civilization exists 70,000 years from now, while the probe was still in transit. That is not a discouraging number. It is a clarifying one. It transforms the problem from something vague and distant, a challenge for some future generation with better technology, into something precisely defined. A hard problem with identifiable constraints and identifiable walls, and hard problems with identifiable constraints can be examined carefully. Their walls can be mapped. Sometimes those walls turn out to have doors. To understand where those doors might be, you first need to understand what the speed of light actually is. Not just that it is fast, what it is, why it is a wall, and not simply a high-speed limit. In 1905, Albert Einstein published a paper that changed the structure of physics. He was 26 years old, working as a patent examiner in Bern, Switzerland, having been unable to find an academic position after graduating. The paper was on special relativity, and it was not primarily about how fast light moves. It was about the geometry of reality, about the precise way that space and time are not two separate, independent things, but two aspects of a single, 4-dimensional structure he called space-time. In everyday experience, space and time feel completely different. Space is the 3-dimensional stage on which things exist. You can move through it in any direction, at whatever speed you choose, stopping and starting and changing direction freely. Time is the single dimension along which events occur. You move through it in only one direction, forward, at a rate you cannot vary, regardless of what you do. The two seem to have nothing to do with each other. Einstein showed that this intuition, which works perfectly at the speeds and scales humans naturally inhabit, is an approximation. At its most fundamental level, reality is not 3 dimensions of space and a separate 1 dimension of time. It is 4 dimensions of space-time, a unified geometric structure in which space and time are 2 faces of the same coin. And the constant that governs the relationship between them, the conversion rate between distance and duration at the most fundamental level of physical reality, is the speed of light. Move faster through space, and you move slower through time. This is not a perception or a clock measurement artifact. It is a consequence of the geometry of space-time itself. The faster you move through space, the more of your 4-dimensional motion is directed along the space dimensions, and the less remains for the time dimension. Time literally passes more slowly for faster-moving objects. This prediction has been tested against atomic clocks flown on aircraft and aboard satellites. It has been tested in particle accelerators where unstable particles moving near light speed have measurable lifetimes far longer than the same particles at rest. The tests always confirm the prediction. Always. Precisely. The speed of light is the constant in this trade-off, and it is why the speed of light is a wall and not just a very fast speed limit. For any object with mass, the energy required to accelerate it further increases without limit as its velocity approaches the speed of light. At 90% of light speed, the energy required to push a kilogram slightly faster is roughly 2.3 times what was needed to get it moving at all. At 99%, about 7 times. At 99.9%, about 22 times. At 99.99%, about 71 times. At 99.999%, about 224 times. The curve is not steep in a manageable sense. It is approaching vertical. At light speed itself, for any object with mass, the required energy is not enormous. It is infinite, not a large number, the concept of infinity. A mathematical statement that the universe contains no finite energy that would be sufficient. The wall is not a cliff, it is a surface that never ends, and behind the energy wall a second wall waits, a logical one. If you could somehow exceed the speed of light through space, the mathematics of special relativity demonstrates that in certain reference frames, valid perspectives occupied by real observers moving at the right velocity, your arrival at the destination would occur before your departure, effect before cause. And if that is possible even once, it is possible to chain two such journeys together to transmit information into your own past. A message that arrives before it was sent. A message that could prevent the decision to send it. Which means it was never sent. Which means it never arrived. Which means the prevention never happened. The loop closes on itself. Physicists call this a causality violation. A closed, time-like curve. A loop in space-time in which a moment connects back to an earlier version of itself in a way that generates unresolvable logical contradiction. Stephen Hawking proposed a principle he called the chronology protection conjecture, the idea that the laws of physics, at some deep level, prevent closed time-like curves from forming. The universe, he suggested, conspires to protect the integrity of its own timeline, but it is still a conjecture, a well-motivated, widely accepted conjecture, not yet a proven theorem. And the fact that it needs to be stated at all, that the universe apparently requires a protection mechanism against its own logical self-contradiction, tells you something important about the depth of the connection between faster-than-light travel and time. They are not two separate problems that happen to be difficult. They are the same problem, seen from different angles. And yet, despite the infinite energy wall, despite the causality paradox, despite every constraint that falls out of the equations when you look carefully, those same equations permit something. Not movement through space at superluminal velocity in the classical sense. Something more subtle. Something that technically does not break any local rule, and yet produces an effect that, from the outside, is indistinguishable from travelling faster than light. Before we get there, we need to understand why the obvious approach, the approach that says simply go faster, carry more fuel, push harder, fails completely. Not partially, not expensively, completely. Here is another way to feel the distance. The radio signals we have been broadcasting since the dawn of radio, the earliest of which left Earth around 1900, have now travelled roughly 124 light-years in every direction. That is the current radius of what astronomers call our radio bubble. Everything within that sphere has, in principle, had the opportunity to receive our transmissions. That bubble contains several thousand stars, and we have received nothing back. But 124 light-years is still 0.12% of the galaxy's diameter. Our radio signals have not yet reached most of the Milky Way. The vast majority of stars in the galaxy have never had any opportunity to detect us. The vast majority of any civilizations that might exist are, at this moment, as completely unaware of our existence as we are of theirs. This is what the scale of the galaxy means in practical terms. Not merely that the distances are large, but that even electromagnetic signals travelling at the maximum speed the universe permits have barely begun to cross them on any timescale relevant to human civilization. The light leaving Earth right now will not reach the centre of the galaxy for another 26,000 years. It will not reach the far side of the Milky Way for nearly 100,000 years. Light is the fastest courier the universe offers, and light itself is slow on galactic scales. The obvious answer to the distance problem is simple. Go faster, build a bigger engine, carry more fuel, push harder, cut the 73,000-year journey to something a civilization can plan around. A century, a generation, a human lifetime. If Voyager is too slow, build something faster. If that is still too slow, build something faster still. We have done this with every other distance problem in history. Ocean crossings that took months by sailing ship took days by steamship, then hours by airplane. Each time we needed more speed, we built a better vehicle. The same progress must apply here. But space does not cooperate with this logic. The failure does not require exotic physics or quantum mechanics or anything beyond basic mechanics. It requires only arithmetic, specifically a single equation derived in 1903 by a nearly deaf Russian mathematics teacher named Konstantin Tsiolkovsky, working in near isolation in a small city south of Moscow, whose ideas about space travel were largely dismissed during his lifetime, and whose equation has governed every rocket launched to this day, unchanged and unreplaced. Tsiolkovsky was born in 1857, the son of a Polish forester employed by the Russian government. At age 10, he contracted scarlet fever and lost most of his hearing. The deafness cut him off from formal schooling. He could not attend the gymnasium, the secondary school that would have been his path to university. He taught himself mathematics and physics from whatever books he could find in Moscow's public libraries, reading voraciously in near total silence, developing ideas in isolation about problems that almost no one in his era took seriously. The colonization of space, propulsion by rocket exhaust, the mathematics of orbital motion. He became a mathematics teacher in Kaluga, writing papers in his spare time that he published in small Russian scientific journals that barely anyone read. In 1903, in the same year the Wright brothers flew at Kitty Hawk, Tsiolkovsky published a paper containing what is now called the Tsiolkovsky rocket equation. It answers a deceptively simple question. If you want to change your velocity by a certain amount, and your engine works by expelling mass out the back of the vehicle at a certain exhaust velocity, how much propellant do you need to carry? The relationship between those three quantities is exponential, not linear, not proportional, exponential. And in the context of reaching interstellar velocities, that exponential character is everything. To accelerate a spacecraft to 1% of the speed of light, roughly 1,860 miles per second, using a nuclear thermal rocket engine, which represents a significant improvement over any propulsion system we have actually built and operated, you need a mass ratio of roughly 3:1. 3 kilograms of propellant for every kilogram of spacecraft and payload. A vehicle that at launch is 3/4 fuel and 1/4 everything else. That is large but not unimaginable. Heavy lift rockets have been built with comparable proportions, but 1% of light speed takes more than 400 years to reach Proxima Centauri. That is not a human timescale. That is not even an institutional timescale. To reach 10% of light speed, which cuts the journey to about 42 years, the mass ratio climbs to roughly 100:1. 100 kilograms of propellant for every kilogram of spacecraft and payload, a vehicle that is more than 99% fuel by mass at the moment of launch. To reach 20% of light speed, reducing the journey to about 21 years, the required propellant mass leaves the domain of engineering. Numbers that have no counterpart in anything humanity has ever built or could realistically consider building, and every one of those calculations assumes the ship only needs to accelerate outbound and then drift to the destination without slowing down. To actually stop at the destination, which is generally considered necessary if you want to do anything useful once you arrive, you need to expend roughly the same amount of propellant a second time. There is nothing at Proxima Centauri to brake against, no atmosphere to aerobrake through, no conveniently positioned gravitational field to absorb your kinetic energy. You carry your braking system from Earth, which means you had to accelerate that braking propellant outbound, which required additional launch propellant, which required propellant to accelerate that propellant, which required propellant to accelerate that propellant's propellant. The equation recurses at every level, and each level multiplies the total mass requirement. This is the rocket equation. It sits quietly at the center of every interstellar mission proposal that has ever been seriously developed and multiplies the required fuel until the mission collapses under its own mass. It explains why chemical rockets are not merely inadequate for interstellar travel, but categorically disconnected from the problem. The Saturn V rocket, the most powerful launch vehicle ever successfully operated, which accelerated human beings on a trajectory to the moon, reached a peak velocity of about 25,000 miles per hour. That is 0.003% of the speed of light. If you plotted a graph with 0 at the left edge and light speed at the right edge, the Saturn V's maximum velocity would appear as a mark less than 1 pixel wide, pressed against the left border, essentially indistinguishable from not moving at all. Chemical rockets do not provide a starting point that can be improved toward interstellar capability. The gap is not a factor of 10 or 100 that better engineering could close. The gap is a factor of millions, and the rocket equation means that closing it by carrying more propellant is not a path. Every additional unit of propellant you load also needs to be accelerated, which requires more propellant, which needs more propellant, without useful limit. This drove the physicists and engineers who took interstellar travel seriously in the second half of the 20th century to abandon chemical propulsion entirely and look for fundamentally different mechanisms. Robert Bussard, a physicist who spent most of his career on nuclear fusion research, proposed the interstellar ramjet in 1960. A ship with an enormous electromagnetic scoop extending thousands of kilometers ahead of it, sweeping up hydrogen from the interstellar medium and feeding it directly into a fusion reactor. The appeal was powerful. The fuel is everywhere. The universe itself provides it. You never carry it with you, so the rocket equation never applies. The faster you go, the more hydrogen you collect per second. The more thrust you generate, the faster you accelerate. An elegant and self-reinforcing cycle. Physicists studied the Bussard ramjet seriously for decades. The problems accumulated. The interstellar medium, though continuous, is extraordinarily sparse, averaging roughly 1 atom per cubic centimetre, and much of that is ionized plasma that does not fuse cleanly under practical conditions. The electromagnetic scoop required to collect meaningful quantities of hydrogen from such a thin medium would need to be maintained against the continuous drag force of the medium the ship is pushing through, and energy analyses generally found that the drag force from the scoop likely exceeds or closely approximates the thrust generated by fusing the collected hydrogen. Some careful analyses concluded that a Bussard ramjet would decelerate rather than accelerate across most of the relevant operating range. The concept pointed in an important direction, that the fuel should not come from Earth, but the specific implementation does not appear to work. Project Orion was conceived on completely different principles. In the late 1950s and early 1960s, a team of remarkably talented physicists at General Atomics in San Diego developed a serious, detailed technical proposal to propel a spacecraft using nuclear bomb detonations. Not as a metaphor, literally. The ship would carry thousands of nuclear charges. Each would be detonated a short distance behind the ship, behind a massive pusher plate of thick steel. The pressure pulse from each explosion would hit the plate and push the ship forward. Spring and damper shock absorbers mounted between the pusher plate and the crew compartment would smooth the succession of rapid impulses into something close to smooth, continuous thrust. The team included Freeman Dyson, one of the most brilliant and versatile theoretical physicists of the 20th century, and Ted Taylor, one of the most creative nuclear weapon designers in American history. They were not fantasizing. They were engineering. Subscale tests using conventional explosives and aluminum pusher plates confirmed the basic concept in laboratory conditions. The impulse transferred from the explosion to the plate matched the theoretical predictions quantitatively. The engineering challenges of the full nuclear system were real, but the team identified no physics prohibitions. Freeman Dyson calculated that an Orion vehicle roughly the size and mass of a small naval destroyer could reach about 3% of light speed using the nuclear technology available in 1960. A larger version, a design Dyson called the Super Orion, scaling up to hundreds of thousands of tons, could in principle reach 10% of light speed. At 10%, Proxima Centauri is 42 years away. Project Orion was cancelled in 1963. Not because the physics failed, not because an engineering impossibility was discovered, because the Partial Nuclear Test Ban Treaty of that year prohibited nuclear detonations in the atmosphere, in space, and underwater. The project was stopped by international law. The United States, the Soviet Union, and the United Kingdom signed the treaty in August 1963. Orion was dead within months. Some of the people who had worked on it never entirely accepted the finality of that outcome. Freeman Dyson called it the moment when the future was cancelled. Project Daedalus, completed by the British Interplanetary Society after 5 years of detailed engineering work from 1973 to 1978, chose inertial confinement fusion. Small pellets of deuterium and helium-3 injected into a reaction chamber at high frequency and ignited by high-powered electron beams would be detonated continuously, producing a directed exhaust of hot plasma. The target was Barnard's star, 5.9 light-years away. The mission was an unmanned flyby, reaching the target in about 50 years while travelling at roughly 12% of light speed. The engineering team worked through the design in detail. They calculated mass budgets and structural loads and propellant flow rates and communication delays and instrument packages. They found no physics prohibitions. The design was internally consistent and technically rigorous by the standards of its time. It was one of the most detailed interstellar mission studies ever completed. but the required propellant was 50,000 metric tons of helium-3. Total global production of helium-3 on Earth amounts to a few kilograms per year. The only plausible source of 50,000 metric tons would be Jupiter's atmosphere, which contains it in small but consistent proportion. Extracting it would require a mining infrastructure in Jupiter's upper atmosphere that does not exist, that would take decades or centuries to build, and that would itself consume resources far beyond anything our civilization has ever assembled. Every serious interstellar propulsion study follows the same arc. The physics is not categorically forbidden. The engineering is conceptually possible, at least at the level of individual systems. The scale required exceeds current civilization's capacity by enormous margins, and every attempt to reduce that scale by increasing propulsion efficiency hits the same wall. More exhaust velocity means more exotic and energetic propellant, and more exotic propellant introduces new engineering challenges that bring their own mass penalties. There is one more problem that tends to be underweighted in these discussions. At any significant fraction of light speed, communication between a mission and its home civilization becomes a civilizational commitment with no historical precedent. A probe to Alpha Centauri at 10% of light speed takes 42 years to arrive. The confirmation signal takes another 4.3 years to reach Earth. 46 years from launch before we know whether the probe survived. If something goes wrong in transit, any problem that requires a response, by the time a corrective command reaches the probe, the problem has been developing for decades without intervention. The mission demands that a civilization maintain focused, continuous institutional commitment to a single specific technical program for 46 years. Through multiple changes of government, multiple shifts in scientific priority, multiple generations of engineers and administrators and oversight bodies, the same basic mission structure must be preserved and resourced. The same antenna arrays must remain operational and pointed in the right direction. The same software infrastructure must be maintained and updated. The same institutional memory must be preserved about what the probe was designed to do and how to interpret what it sends back. We have no demonstrated capacity to do this. The longest focused technical programs in human history are measured in decades. Major scientific facilities like CERN have operated for decades and maintained institutional continuity. But CERN produces results continuously and has institutional renewal built into its structure. A one-way interstellar probe operating in radio silence for 42 years is a different kind of commitment. We have not made one successfully. The problem is not just reaching the destination. It is arriving there with functioning instruments and having a civilization back home still organized and prepared and caring enough to receive what was found. There is one more dimension to this problem that rarely receives the attention it deserves, because it involves not physics but organizational capacity. Suppose a drive system were developed that could accelerate a crewed ship to 10% of light speed. The journey to Proxima Centauri would take roughly 42 years, plus 42 years to decelerate and return, plus time at the destination, a minimum of 90 to 100 years for a complete crewed round-trip mission. No human alive at departure would be alive at the return. The crew of the return ship would be the children or grandchildren of the people who left. The mission would require not just building a ship but creating a self-sustaining multi-generational community capable of maintaining purpose and coherence across multiple generations in total isolation, with no resupply and no possibility of turning back past a certain point. We have never done this. The longest continuous crewed spaceflight ever conducted lasted about 14 months. A multi-generational interstellar mission would require something qualitatively different from anything in the human record. A civilization within a civilization. A community designed from the ground up to survive in isolation for a century, while maintaining a defined scientific mission through generational change. The rocket equation is a mathematical problem. The human dimension of interstellar travel is something harder to quantify and in some ways harder to solve. But there is another way to approach the distance problem entirely. If brute force fails, and it does, the next question is whether we can cheat the distance itself. Not push an object faster through space, change what space does. Alter the geometry of the medium rather than the velocity of the object moving through it. This is where the warp drive enters the story. And I want to be precise about what that means, because the phrase has accumulated so much science fiction association that it takes effort to hear it as technical description. The warp drive I am describing is not a plot device. It is a specific mathematical object, a solution to a specific set of equations. It was first described in rigorous technical terms by a Mexican physicist named Miguel Alcubierre in a paper published in the journal Classical and Quantum Gravity in 1994. Alcubierre was 32 years old and completing his doctoral work at the University of Wales when he wrote the paper. He had been watching an episode of Star Trek, the television program, and found himself wondering whether the concept of a warp drive could be made internally consistent with general relativity. He was not expecting the answer to be yes, but it was. To understand what Alcubierre found requires one piece of general relativity that sounds simple, but contains a great deal. General relativity, published by Einstein in 1915, extended special relativity to include gravity and acceleration. Its central insight is that gravity is not a force in the sense Newton described. It is the curvature of space-time caused by the presence of mass and energy. Objects moving through curved space-time follow the most efficient paths available to them, the paths that minimize the four-dimensional equivalent of distance in the geometry. These paths, called geodesics, appear curved to an outside observer when the underlying space-time is curved. The Earth orbits the Sun not because a gravitational force reaches across 93 million miles and pulls it. The Earth follows the most efficient path through a region of space-time curved by the Sun's mass. The Moon orbits the Earth for the same reason. Light bends around massive objects for the same reason. The GPS satellites in orbit run their clocks slightly fast relative to clocks on the ground because time passes at a different rate in the gravitational field at orbital altitude than at Earth's surface, a direct consequence of the same space-time curvature. Einstein's field equations, the mathematical heart of general relativity, describe the relationship between the distribution of matter and energy and the resulting geometry of space-time. They are extraordinarily general. Given the right distribution of matter and energy, the equations will produce almost any space-time geometry you can specify. Space-time that expands, space-time that contracts, space-time that curves so severely it folds back on itself and forms a black hole, space-time that propagates distortions outward as gravitational waves. Almost any geometry you can write down mathematically, the equations will tell you what distribution of matter and energy would produce it. What Alcubierre asked was whether any geometry of space-time exists that would allow something to travel between two distant points in less time than light would need to cross that distance in flat, undistorted space-time, without that something ever exceeding the speed of light in its own local neighbourhood. The answer he found was yes. The Alcubierre metric describes a specific space-time geometry, a region of flat, undisturbed space-time forming the interior of what has been called a warp bubble. Surrounding that flat interior, a shell of distorted space-time. Inside the flat interior, physics is completely normal. An observer there would feel no acceleration. Their instruments would function exactly as expected. Their clocks would tick at a normal rate. Nothing inside the bubble would violate any rule of special or general relativity at the local level. The observer would have no direct experience of anything unusual. But outside the bubble, the geometry of space-time is being dynamically changed. Space ahead of the bubble is contracting. Space behind the bubble is expanding. The net effect is that the bubble, with everything inside it, is carried forward by the motion of the surrounding space-time itself, the way a surfer is carried forward not by pushing quickly through the water beneath them, but by riding the forward motion of the wave. The surfer does not move fast relative to the water at their immediate location. The water moves, the surfer goes with it. From the perspective of a distant observer watching the ship depart from Earth and arrive at Proxima Centauri, the ship appears to have crossed 4.24 light-years, in a time much shorter than light could cross that distance in flat space. Perhaps a year, perhaps months, perhaps in the most aggressive versions of the geometry much less. And nothing local violated any rule. Space moved. The ship rode it. This is not a metaphor or a science fiction shorthand. The Alcubierre metric is a genuine solution to Einstein's actual field equations. The same field equations that correctly predicted, decades before the first detection, the existence of gravitational waves, the ripples in space-time produced by accelerating massive objects. In 2015, the LIGO detectors first measured gravitational waves produced by the merger of two black holes over 1 billion light-years away, confirming a prediction Einstein had made a century earlier. The same field equations that require GPS satellite clock corrections applied in every GPS calculation today. These equations have been tested against physical reality repeatedly and precisely across a remarkable range of predictions. They permit the Alcubierre geometry. The question is whether the geometry can be physically produced, and there the obstacles begin. The original Alcubierre formulation requires to create the needed spacetime curvature matter with negative energy density. Not matter at very low temperature, not matter with low kinetic energy, matter with less energy per unit volume than the vacuum of completely empty space. Negative energy, less than nothing. This sounds like a fictional construct, a mathematical placeholder with no physical meaning. But negative energy density is not fictional. It has been observed in a laboratory. The phenomenon is called the Casimir effect, named after Dutch physicist Hendrik Casimir, who predicted it in 1948 while working at Philips Research Laboratories in the Netherlands. The Casimir effect arises from the quantum nature of the vacuum. According to quantum field theory, the vacuum of space is not truly empty. It is filled with quantum fluctuations, virtual particle-antiparticle pairs briefly appearing and disappearing, a background of zero-point energy that carries small but real physical effects. Between two flat, electrically neutral, closely spaced metal plates placed in a near-perfect vacuum, the quantum fluctuations that can exist are restricted. Only fluctuations with wavelengths that fit between the plates are permitted by the boundary conditions imposed by the metal surfaces. Outside the plates, the full spectrum of fluctuations is present. The energy density between the plates is therefore measurably lower than the energy density of the surrounding vacuum, lower than empty space, negative in the relevant physical sense. This energy difference produces a small but real force pushing the two plates together. Casimir predicted the magnitude of this force precisely from first principles. Experimental confirmation came in the 1950s, with higher precision measurements in the late 1990s by physicist Steve Lamoureux and others, confirming the theoretical prediction to a precision of better than 5%. The Casimir effect is real. Negative energy density is real. It exists in the physical world. It has been measured. The problem is scale. Alcubierre's original calculation estimated the exotic matter requirement for a warp bubble large enough to enclose a useful spacecraft at a mass energy equivalent, roughly comparable to the total mass energy of the planet Jupiter, but negative. Jupiter has a mass of approximately 1.9 times 10 to the 27th kilograms. Its total mass energy, computed via Einstein's mass energy equivalents, is an immense number expressed in joules. We would need that much negative energy density, precisely arranged in a specific geometric configuration around a spacecraft. The Casimir effect produces negative energy density in quantities so vanishingly small that scaling from measured laboratory values to Jupiter mass equivalents is not an engineering challenge. It is a ratio that ordinary language about size does not have the vocabulary to express accurately. The gap is more like comparing the charge of a single electron to the total electric charge of all the matter in the observable universe. Not large, not very large, a ratio whose magnitude defies description. For roughly a decade after Alcubierre published, most physicists treated the warp drive as a mathematical curiosity. A demonstration of what the equations allow in principle, filed alongside other exotic solutions like wormholes and traversable cosmic strings, interesting to study but not physically relevant. The exotic matter requirement was considered a categorical showstopper, and then researchers started examining the assumptions more carefully. Harold White, a physicist at NASA's Johnson Space Center, began around 2011 to ask whether the exotic matter requirement was a fixed physical constant or an artifact of the particular geometry Alcubierre had chosen. The original solution used a relatively simple warp bubble geometry, a spherical shell of distorted spacetime with roughly uniform thickness and a specific curvature profile. White began systematically varying the geometry. He tried thinner shells. He tried toroidal distributions of the curvature. He tried geometries where the bubble walls oscillated dynamically rather than remaining static. His revised calculations suggested that the exotic matter requirement was sensitive to the geometry of the bubble. Different geometries produced significantly different requirements. The flaw was not where the original paper had placed it. White's specific calculations were subsequently challenged by other physicists. Some of his proposed reductions were found not to hold under more rigorous scrutiny. The precise quantitative magnitude of any improvement remains disputed and uncertain. But the directional finding that the requirement is a design parameter rather than a fixed physical constant opened a line of inquiry that has continued. In 2021, Eric Lentz, a physicist then at the University of Göttingen, published a paper in Classical and Quantum Gravity proposing a genuinely new class of warp solutions. He had been explicitly searching for geometries that required only positive energy, not exotic matter, not negative energy density, ordinary positive energy of the kind that exists everywhere in the universe in unlimited supply. He found a class of self-contained, stable spacetime configurations that he called hyperfast solitons, compact waves of curved spacetime that he argued could produce a warp-like propulsive effect, using only positive energy sources arranged in specific geometric patterns. If Lentz's solutions are physically valid, and the detailed implications are still being analysed and debated in the literature, the character of the exotic matter problem changes entirely. It shifts from a categorical requirement, something the physics demands that does not exist at useful scales, to a specific implementation that may be avoidable with the right geometry. A warp mechanism that requires only positive energy is in a fundamentally different category from one requiring negative energy, because we know in principle how to generate positive energy. We do it continuously, in nuclear power plants and chemical combustion and solar panels and every other energy technology we have. The problem shifts from categorically impossible to merely very hard. That is not a small shift. More recently, researchers at a group called Applied Physics published analysis suggesting that a warp bubble too small to contain anything, but in principle large enough to be detected by a sensitive laboratory instrument, might require energies not impossibly beyond what current experimental physics already routinely handles. Not building a ship. Building an experiment. A measurement. A confirmation that the mathematics corresponds to something the physical universe actually permits. That step from mathematical permission to laboratory test is the step that every physical theory must pass through on its way from equations to technology. But the exotic matter problem is not the only wall buried in the mathematics. A warp bubble moving at superluminal speeds does not move through the quantum vacuum passively. As the bubble moves forward, the geometry of contracting spacetime at its leading edge accumulates energy from the quantum vacuum. The same zero-point energy structure that gives rise to the Casimir effect is present throughout all of space, and a rapidly moving bubble geometry compresses it at the leading edge, concentrating high-energy virtual particles that cannot escape forward because the contracting geometry is sweeping through them faster than they can travel. They pile up. They ride the leading edge of the bubble throughout the journey, building in energy. When the bubble reaches its destination and the warp effect is switched off, those accumulated particles are released, all at once, in a burst directed forward toward whatever is in front of the ship at the moment of arrival. The energy of that burst may be comparable to a nuclear weapons yield, or larger, depending on the duration and speed of the transit, and it is directed at the destination, at whatever planet or station or civilization exists at the arrival point. The act of arriving may destroy the thing you arrived to visit. This is not an engineering flaw that better insulation can fix. It appears to be a structural consequence of how a moving warp bubble interacts with the quantum vacuum throughout transit. Addressing it would likely require a fundamentally different class of bubble geometry, one that has not yet been identified. And then there is the isolation problem. Inside a warp bubble, the interior region is geometrically sealed from the surrounding universe. The spacetime geometry of the bubble prevents electromagnetic signals from crossing the bubble boundary in either direction. The crew inside cannot observe what is ahead of them. They cannot receive updated trajectory data from home. They cannot steer in response to new information. They cannot brake or slow down. They set their course before departure, activate the bubble, and travel to wherever the bubble was aimed, arriving at whatever moment the physics delivers them there. Sealed inside a room moving through space they cannot observe or interact with, toward a destination they aimed at before they left, with no ability to respond to anything that changes between departure and arrival. The warp drive, in its current theoretical state, does not eliminate the wall between here and Proxima Centauri. It moves the wall. It creates multiple walls in different locations, the exotic matter problem, the vacuum radiation released on arrival, the causality paradoxes at true superluminal speeds, and the navigational isolation. Each wall is different in character from the original. Each requires a different approach. None of them is resolved. But they are different in character from the infinite energy wall of special relativity. They are specific obstacles, not categorical prohibitions. And that difference, between specific obstacle and categorical prohibition, is the difference between a problem that research can work on and a problem that research cannot penetrate. The conversation has changed. There is one aspect of the warp drive physics that tends to get overlooked in popular discussions, and it concerns the boundary of the bubble itself. In the original Alcubierre formulation, the transition between the flat interior and the distorted shell occurs over a very short distance. At that boundary, the gradient of space-time curvature is enormous. Anything crossing that boundary encounters this gradient at full force. This creates a navigation problem that goes beyond the communication blackout already described. If anyone inside the bubble tried to observe the outside universe using any sensor or telescope, the extreme curvature at the boundary would severely distort any information attempting to cross it. The crew would not be merely unable to communicate, they would be effectively blind. A warp-capable civilization would need to map their entire trajectory in advance, with sufficient precision to guarantee that no obstacle would be present along the path during transit. For a journey to Proxima Centauri, that trajectory spans 4.24 light-years of space, containing the interstellar medium, potentially rogue planets, uncharted dense regions, and objects not yet catalogued from Earth. Mapping that path at the resolution required for safe transit is, at minimum, a multi-decade project using instruments more capable than anything we currently operate. The warp drive is not just a propulsion problem, it is an information problem, a navigation problem, a safety problem, and a weapons problem. Each is real and distinct and none has a solution. Even if the engine worked, even if the exotic matter was found and shaped and held in precise configuration, even if the bubble geometry could be controlled and navigated and safely collapsed at the destination, even if every theoretical obstacle inside the mathematics was resolved tomorrow, the universe would still be trying to destroy the mission from the moment it entered interstellar space, not passively, not through the indifference of empty space. Actively, through physical mechanisms that grow more severe the faster the ship moves, each one demanding its own engineering response, each response adding mass, each additional mass making at least one other problem incrementally worse. Picture the ship crossing the dark between stars at 20% of the speed of light. Not warp speed, not relativistic extremes, just 20%. A velocity that serious interstellar engineering proposals consider potentially achievable within the next century or two with sufficient technological development. Ahead of the ship, the darkness appears empty. It is not. Interstellar space contains what astronomers call the interstellar medium, a diffuse mixture of gas and dust distributed throughout the galaxy, present everywhere, thinning in the voids between spiral arms and thickening in molecular clouds, but never absent. Mostly hydrogen, mostly ionized into free protons and electrons, some helium, traces of heavier elements sputtered off by stellar winds and scattered through the galaxy across billions of years, silicate and carbonaceous dust grains, complex organic molecules. Amino acids have been detected in interstellar molecular clouds. The average density in our region of the Milky Way is roughly 1 atom per cubic centimetre. At the speeds of current spacecraft, the interstellar medium is harmless. Voyager. One has been crossing regions of comparable particle density for over a decade without meaningful damage to any of its instruments. The particles drift past at such low relative velocity that their kinetic energy on impact is negligible, far below the threshold of any harm. At 20% of light speed, everything changes. From the ship's reference frame, each hydrogen atom encountered is not a slowly drifting particle. It is a projectile arriving at approximately 37,000 miles per second. Its kinetic energy on impact is about 400 million electron volts per proton. That is the energy range of cosmic rays capable of penetrating significant thicknesses of shielding material and depositing damaging radiation doses in electronics and biological tissue. A single interstellar dust grain, a silicate particle perhaps 1 micrometer across, carries the kinetic energy of a small explosive charge. Not large by weapon standards, but not harmless by any standard that matters for a spacecraft or a crew, and the encounters are not rare events. At 20% of light speed, a ship with a cross-sectional area of 1 square meter sweeps through the interstellar medium fast enough to encounter roughly 100,000 hydrogen atoms every second. Over the course of a 20-year journey, the cumulative particle flux through any exposed surface is enormous. An unshielded biological crew would reach a lethal radiation dose within hours of reaching full speed. The hull surface would erode steadily and continuously, material being sputtered away by each impact like the surface of a metal plate in a particle accelerator beam. Shielding is the standard engineering response, and it works within limits. A layer of dense particle-stopping material placed at the front of the ship absorbs incoming ions before they reach critical components. The Daedalus study included a beryllium erosion shield designed to survive the particle bombardment of a 50-year flight at 12% of light speed. The Breakthrough Starshot program has devoted substantial research attention to protecting a gram-scale probe from dust impacts at a fifth of light speed. The approaches differ because the spacecraft scales differ, but the underlying engineering is the same: physical mass interposed between the hazard and the thing being protected. Shielding adds mass. Mass requires more energy to accelerate. More energy requires more propellant. And the rocket equation, which was already the primary obstacle to interstellar travel, reappears in a new form, pressing the same constraint from a different direction. Every engineering solution to the interstellar radiation hazard is a transaction with the rocket equation, but shielding cannot address the hazard that emerges at higher speeds. The cosmic microwave background radiation fills the entire observable universe. It is the thermal afterglow of the Big Bang, cooled by 13.8 billion years of cosmic expansion from its original enormous temperature down to its current temperature of 2.7 Kelvin. At that temperature, from the perspective of any observer at rest, it consists of microwave photons so cold and low energy that they pass through everything without perceptible effect. We are immersed in the CMB continuously. We cannot feel it. We cannot detect it without specialized instruments. It is as invisible and as harmless as the lowest possible hiss of radio static. But from the perspective of a ship moving at high velocity, the CMB photons arriving from ahead of the ship are blue-shifted. Their apparent wavelength compresses. Their apparent frequency rises. Their apparent energy increases. The faster the ship moves, the more severe the blue shift. At 50% of light speed, the CMB ahead appears as infrared radiation, higher energy than microwaves, but still well below any threshold of biological harm. At 70% of light speed, it appears as near ultraviolet. At 90% of light speed, it appears as soft X-rays. The crew is now inside what would ordinarily be called an X-ray radiation environment, receiving a continuous dose from the forward hemisphere, from the ambient background radiation of the universe itself, without any shielding that could realistically be carried. At a somewhat higher fraction of light speed, the apparent energy of the CMB photons crosses into hard X-rays and then into gamma radiation. Hard gamma radiation penetrates conventional shielding materials far more effectively than charged particles do. There is no practical thickness of any material commonly proposed for spacecraft construction that stops hard gamma radiation at the intensities involved. Any biological crew would receive a lethal dose within minutes. Electronics would be degraded within seconds. This creates an absolute ceiling on safe travel speed for biological organisms that has nothing to do with propulsion capability and nothing to do with the warp drive problem. The universe itself, through the background radiation left over from its own origin, sets a hard limit on how fast anything alive can move through interstellar space. That ceiling sits somewhere below 90% of light speed, likely significantly lower when you factor in acceptable dose rates and mission duration and the practical mass of any shielding that might reduce but not eliminate the exposure. And it cannot be engineered around simply by adding more shielding, because the massive shielding required would be so large that the rocket equation would collapse the mission before the radiation ceiling was ever relevant. There is also the galactic magnetic field. The Milky Way maintains a diffuse magnetic field permeating its entire volume. Extremely weak by ordinary standards, measured in microgauss, millions of times weaker than the Earth's field. Under normal conditions, it exerts no measurable force on spacecraft, but a spacecraft moving at high velocity through a magnetic field encounters, from its own reference frame, an electric field as well. The relativistic transformation of electromagnetic fields produces an electric component whenever there is relative motion between the observer and the field source. At fractions of light speed approaching those relevant to interstellar travel, the induced electric field accelerates charged particles toward the ship at energies comparable to those produced in particle accelerators. The ship is, in effect, continuously irradiating itself as a consequence of its own motion through the galaxy's ambient magnetic field. This hazard is independent of and in addition to the dust impacts and the CMB blue shift. It has its own dose rate profile and its own engineering demands. These hazards do not add together as simple independent contributions, they compound. Shielding against charged particles adds mass. More mass means more kinetic energy per unit of hull area when dust impacts strike the shielding, which requires heavier shielding, which requires more propellant, which adds more mass, which strengthens the interaction with the magnetic field, which adds to the radiation dose. Every solution to every problem makes at least one other problem incrementally worse. The engineering space available for a viable interstellar mission narrows with every additional increment of speed. The universe does not become more neutral as you accelerate, it becomes more hostile, and the hostility is systematic, not random. It targets exactly the capabilities a useful mission needs: crew survival, instrument integrity, hull durability, and the propellant margins required to address everything else. The faster we go, the less empty space becomes. All of these hazards operate on the ship from outside. They are environmental. They have engineering responses, even if those responses are expensive and compounding. There is one more cost that these engineering responses cannot touch at all. One that operates not on the hull, but on the relationship between the mission and the civilization that launched it. A cost that grows with velocity not because the environment becomes more hostile, but because time itself begins to behave differently for anyone moving very fast through space-time. The crew might survive the crossing, the ship might hold, the instruments might function, the mission might succeed in every measurable sense. The world they left behind might not survive the weight. To appreciate the full compounding nature of these hazards, consider what a viable crewed interstellar mission profile actually looks like when all constraints are imposed simultaneously. Biological humans need air, water, food, temperature control, radiation shielding, and psychological support. The minimum mass for a life support system keeping a small crew alive for 20 years is estimated at tens of thousands of kilograms, assuming advanced recycling. The shielding required to reduce charged particle and CMB radiation to safe levels at 20% of light speed adds thousands more kilograms. The ship structure supporting all of this adds more still. Now apply the rocket equation to this total mass at 10% of light speed. You would need a propellant mass many times the mass of the International Space Station, which took 13 years and the resources of 15 nations to assemble. A crewed interstellar mission at modest sublight speed requires not just a more powerful engine, but a fundamentally different scale of civilizational investment. This is not an argument that it is impossible. It is an argument for clarity about what it actually requires, and that clarity is part of why faster-than-light travel, rather than simply faster sublight travel, has attracted serious theoretical attention. Even imperfect faster-than-light would change the scale of the problem so fundamentally that the two represent qualitatively different challenges, not merely quantitatively different versions of the same challenge. At low speeds, time is simple. A clock on Earth and a clock aboard a spacecraft mostly agree. GPS satellites orbit at roughly 8,700 miles per hour and must apply relativistic corrections, but those corrections amount to only about 38 microseconds per day. A rounding error by any human standard. A day in orbit and a day on the ground are, for all practical purposes, the same day. But as a ship accelerates toward a meaningful fraction of light speed, the agreement between clocks does not merely drift, it breaks. Not because of instrument error or signal delay or any problem that technology could correct, because the geometry of space-time treats two objects moving at different velocities as genuinely, physically, and permanently experiencing different rates of time. This is not a theoretical prediction awaiting confirmation. It is measured reality. In 1971, physicists Joseph Haefel and Richard Keating flew atomic clocks around the world on commercial aircraft and compared them afterward to reference clocks left on the ground. The airborne clocks showed time differences exactly consistent with the predictions of special and general relativity combined. The experiment has been repeated many times since, with improving precision, always matching the theory. In particle accelerators around the world, subatomic particles travelling at high fractions of light speed have measured lifetimes many times longer than identical particles at rest, exactly as the relativistic time dilation formula predicts. Muons produced by cosmic rays in the upper atmosphere would decay long before reaching the ground if time worked the same way for them as for a particle at rest. Their extended lifetimes, produced by their high velocity, allow them to reach the surface. We detect them routinely. The physics is not a hypothesis. It is the daily operational reality of nuclear and particle physics. The relationship is governed by a formula called the Lorentz factor, input of velocity, and the formula returns the ratio of time experienced by an observer at that velocity to time experienced by an observer at rest. The formula is exact, not approximate, and it has been confirmed against measurement at every velocity where measurement has been possible. At 10% of light speed, the dilation is small. A crew travelling for 1 year of their experience returns to find that Earth aged 1 year and about 2 extra days. A gap, real, but not disorienting. At 30% of light speed, the crew ages at roughly 95% of the Earth rate. A 10-year mission corresponds to about 10.5 Earth years. At 50% of light speed, the crew ages at about 87% of the Earth rate. A 5-year crew journey corresponds to about 5.8 Earth years. At 70% of light speed, the crew ages at about 71% of the Earth rate. A 10-year mission corresponds to about 14 Earth years. At 90% of light speed, the crew ages at roughly 44% of the Earth rate. A 5-year crew journey corresponds to nearly 12 Earth years. Children who are 10 at departure are 22 on the mission's return. Parents who are healthy at departure have aged 12 years in what felt to the crew like 5. At 99% of light speed, 1 crew year corresponds to about 7 Earth years. At 99.9%, 1 crew year is roughly 22 Earth years. At 99.99%, 1 crew year is approximately 70 Earth years. These are not estimates or approximations. They're exact predictions of a confirmed theory, describing what actually happens to physical clocks and biological aging processes and every time-dependent phenomenon, without exception, at every speed that has ever been tested. Consider what this means for a real mission to Proxima Centauri at 90% of light speed. The journey takes about 4.7 years of crew time, 4 years and 8 months of subjective experience. The crew departs, they work, they cross 4.24 light-years of interstellar dark in what feels to them like a little under 5 years. They arrive at the destination, they conduct observations, they collect data, they begin the return journey, another 4 years and 8 months. They arrive back at Earth having personally experienced roughly 9.5 years away. On Earth, 22 years have passed. Children who were 10 when the mission departed are 32 on its return. They were children. They are full adults. They have built careers, relationships and lives in the 22 years since their parent walked out the door. Their parent walked back in looking only about 10 years older. They look 22 years older. Parents who were 60 at departure are 82 on return. Some may have died in the intervening years. Others are in declining health. The most important personal relationships in the crew members' lives have been stretched across a 22-year gap that the crew personally experienced as 9.5 years. The gap cannot be closed. It can only be acknowledged. The research organizations that funded the mission have experienced 22 years of institutional change. Directors have retired. Priorities have evolved. The specific scientific questions the mission was designed to answer may have been addressed by other means in the 2 decades the ship was in transit. The technology the crew was trained on is a full generation out of date. The geopolitical and economic arrangements that supported the program have transformed. The crew returns to a world that is technically the same world they left, populated by many of the same people, but they return to it displaced in their own timeline by 22 years relative to everyone and everything they knew. They are not in a foreign country. They are in their own country, 22 years into a future they did not personally live through. Now push the speed higher to reduce this displacement. At 99% of light speed, the round trip takes the crew about 14 months of subjective time. A long voyage, but not extreme. They return from what feels like a challenging but manageable mission. Earth has experienced 8.6 years. Every increment of additional velocity that compresses the crew's subjective experience of the journey amplifies the displacement between their timeline and everyone else's. To minimize the crew's experience of the journey is to maximize their disconnection from the civilization that sent them. There is no speed at which both problems are solved simultaneously. The physics forbids it. The faster you go, the more you trade one kind of cost for another. The classical name for this asymmetry is the twin paradox. One twin boards a high-speed ship, the other stays home. When the traveller returns, they are younger. Not by perception, not by feeling, by physical measurement, by atomic clock readings, by biological aging, by every process that evolves over time. The resolution in physics is clean and does not require paradox. The travelling twin accelerated and decelerated. The stationary twin did not. The asymmetry in their space-time trajectories is real, not a trick of perspective, and it produces a real and permanent difference in elapsed proper time. The mathematics resolves. The human situation does not. What the mathematics describes, in human terms, is a kind of separation that has no precedent in ordinary experience, not distance, not death, something between them. The traveller is alive, they are intact, they are continuous with the person who left. But the connection between their timeline and everyone else's has been permanently altered by the geometry of the universe in a way that no technology and no engineering can prevent or reverse. And the disconnection runs in both directions simultaneously. Because the ship cannot transmit information faster than light, the messages sent home from the mission arrive at Earth shifted by the compound effect of the ship's velocity and the finite travel time of the signal. In the outbound phase, as the ship accelerates away, successive messages sent at regular intervals arrive at Earth with growing time gaps between them. Each message must travel a greater distance than the previous one. The ship is always partly outrunning its own transmissions. From Earth's perspective, the crew's messages arrive increasingly rarely. The intervals lengthen. The carrier frequency drops as the Doppler effect stretches the signal. The voice of the crew fades, becoming quieter, slower, and more infrequent, like a radio station receding as you drive away from the transmitter. The crew does not disappear from Earth's awareness all at once. They fade, over months and then years, as the intervals between transmissions grow, until at last the gap between messages is measured not in days but in months and years, and waiting for a single transmission from the mission becomes itself a significant portion of a human life. When the ship turns for home and begins decelerating and then accelerating back toward Earth, the process reverses. Messages arrive closer together. The frequency rises. The voice returns, louder, more frequent, closer, until the ship is back in the inner solar system and the delay shrinks from years to hours to minutes. But the 22 years will always have passed. The gap is permanent. It becomes the fixed background condition of every relationship that survives the mission. The twin paradox reveals something about the nature of interstellar travel that goes beyond the physics. Every interstellar mission, if it is crewed, is a negotiation with time itself. The crew chooses to leave their timeline, not accidentally, not as an unavoidable side effect of a journey they might have taken otherwise, as a direct consequence of the velocity required to make the journey possible. The faster the ship, the more complete the departure from the timeline of everyone who stays behind. At 90% of light speed, the crew departs from one timeline and returns to a different one. Not different in the sense of having changed, because all timelines change. Different in the sense of having advanced 22 years while the crew advanced 9.5. Different in the sense of having lived through things the crew did not live through. Different in the sense of having lost people the crew did not lose, and grown people the crew did not watch grow. There are people who would accept this, who would say the mission is worth any cost, including the cost of returning to a changed world, who would say the knowledge gained is worth the relationships altered, and there are people who would not, for whom the disconnection is precisely what makes the journey impossible to choose, no matter what waits at the destination. Faster-than-light travel would remove this choice from the equation entirely. It would make the journey possible without requiring the traveller to leave their own time. That is not a minor convenience. For anyone who loves something on Earth, it is the difference between a journey and an exile. This is why faster-than-light travel matters at a level deeper than engineering and deeper than physics. We do not want to go to the stars and return as visitors to our own civilization. We want to go and come back. We want the journey to be a journey, not a passage out of the only timeline we have ever inhabited. We want to find something extraordinary and bring the knowledge home while the people who wanted to know are still present and able to receive it. Faster-than-light travel, if it could exist, solves this problem in a way that nothing else in the equations allows. A ship that crosses to Proxima Centauri faster than light accumulates no time dilation. It departs, arrives, observes, and returns within a time frame that human relationships can survive. The people who funded the mission, trained the crew, and simply wanted to know what was out there are still there when the answer comes back. That is not primarily a technical appeal. It is a human one, the desire to go and to return, to explore without becoming permanently other, to reach into the dark without being severed from the light behind you. If you're still with us, stay with the crew. There is one more layer to this problem, and it is the one that makes faster-than-light travel feel less like a technical challenge and more like a boundary the universe has placed around all intelligence equally. Not just around us, so now we have to ask the darker question. What if the silence from the stars is not mysterious because no one is out there? What if it is mysterious because everyone has found the same wall? If interstellar travel is this difficult for us, it may be this difficult for everyone. Not because humanity is uniquely primitive or uniquely unlucky. Not because we happen to have emerged at a particularly difficult moment in cosmic history. Because the same universe surrounds every civilization that has ever existed anywhere in the galaxy. The same 299,792 kilometers per second. The same 4.24 light-years to the nearest neighbor from any given starting point. The same exponential propellant requirement. The same interstellar radiation environment that grows more lethal with each increment of speed. The same time dilation that disconnects travelers from their civilization the faster they push. The same causality structure inside the mathematics that waits for anything attempting true superluminal motion. The laws of physics are not local. They do not vary by species or by planet or by moment in time. Every intelligence that has ever evolved in this galaxy has inherited exactly the same set of constraints. This is the lens through which the Fermi paradox deserves to be examined most carefully. In 1950, the physicist Enrico Fermi was eating lunch at Los Alamos National Laboratory with colleagues that included Edward Teller. The conversation had drifted to extraterrestrial intelligence and to a recent series of newspaper reports about unidentified flying objects. Fermi made a rapid mental calculation. The galaxy is roughly 100,000 light-years across and approximately 13 billion years old. It contains between 200 and 400 billion stars. Many of those stars formed billions of years before the Sun. The emergence of complex life on Earth required roughly 4 billion years from the formation of the planet. If even a small fraction of stars have habitable planets, and a small fraction of those develop intelligence, and a small fraction of that intelligence develops interstellar capability, then civilization should have spread throughout the galaxy billions of years ago. Even at very modest sublight speeds, a civilization willing to expand could cross the entire Milky Way in perhaps 10 million years. 10 million years is less than 0.1% of the galaxy's age, and yet the sky is silent. No ships in our skies that require intelligence as their explanation. No signals in our radio telescopes that cannot be explained by natural astrophysical processes. No megastructures partially enclosing the energy output of nearby stars. No artifacts anywhere in the solar system from prior visitors. No anomalies in the geological or biological record that demand an engineering explanation. The silence is consistent and profound, and it has generated more than 70 years of serious scientific and philosophical discussion. The first major family of explanations says the silence reflects rarity. Perhaps the conditions required for life are far more specific than the sheer number of worlds in the galaxy might suggest. The right stellar type, the right distance from a galactic arm, the right planetary mass. The right amount of water, delivered at the right time by the right kind of asteroid bombardment. The right presence of a large moon to stabilize the planet's axial tilt. The right timing of mass extinctions that periodically reset evolutionary trajectories and open ecological niches for new forms of complexity. Perhaps a dozen or 100 other factors, most not yet identified. Perhaps the emergence of technological intelligence from any given biosphere requires such a specific and improbable chain of events, each step individually possible, but together forming a near miracle, that it happens no more than once per galaxy in any given era. The silence is the silence of an effectively empty universe where Earth is genuinely rare, perhaps nearly unique. The second major family says the silence reflects a pattern of self-destruction, that the development of technology sufficient to communicate across interstellar distances is reliably followed, within a geologically brief interval, by the development of technology sufficient to cause civilizational collapse, nuclear weapons, engineered pathogens designed for maximum lethality. Resource exploitation so severe and so rapid that the ecological systems supporting complex civilization fail before the civilization that created the problem develops the coordination to address it. some threshold of destructive capability that intelligent species tend to cross before they develop the wisdom not to use it. If this pattern is reliable, the galaxy is full of civilizations that briefly appear in the radio spectrum, flare with increasingly energetic signals for perhaps a few thousand years, and then go permanently silent. The silence we observe is the statistical consequence of a pattern repeated billions of times. The third major family says the silence reflects undetectability, that civilizations exist and are present but have moved beyond electromagnetic communication into modes we cannot intercept. Tight directional laser beams aimed at specific recipients rather than broadcasting omnidirectionally. Quantum communication channels that leave no detectable background. Physical processes we have not yet imagined. Or that they are present but quiet, for reasons of prudence or philosophy that we would understand if we were at a comparable stage of development. Or that they are simply so far away that their signals have not yet reached us, or reached us before we had the instruments to detect them. Each of these explanations has serious proponents. None is confirmed. Each carries its own distinct implications for what humanity might expect from the future. But there is one explanation that appears rarely in mainstream accounts of the Fermi paradox, possibly because it is the most ordinary of all, possibly because it requires accepting something about the structure of the universe that we would prefer to be otherwise. Maybe the wall is the answer. Maybe intelligence arises in the galaxy with reasonable regularity across billions of years, not on every world, not even on most worlds, but regularly enough that the galaxy has hosted many technological civilizations across its long history. Maybe they develop curiosity in language and mathematics and engineering and radio telescopes and rockets. Maybe they look at the night sky with the same specific longing that we feel, the longing for contact, for confirmation that the silence is not the final word, for the knowledge of what is out there among the stars, and then they run the numbers, and the numbers give them what our numbers give us. The nearest star requires 73,000 years at the speed of the fastest probe. The rocket equation makes brute force interstellar propulsion impractical at any velocity that closes the distance in a human timescale. The radiation environment grows more lethal with every increment of speed. Time dilation disconnects any crew from the civilization that sent them. The mechanisms for faster-than-light travel require either exotic matter that cannot be produced at useful scales, or positive energy at scales no single civilization commands, or both. The causality paradoxes at true superluminal speeds remain unresolved, and maybe most civilizations, not all but most, encounter this calculation and make a rational decision. The resources required to cross even the nearest stellar distance are enormous, and must be diverted from other uses. The probability of a meaningful return on that investment is uncertain. The institutional patience required to sustain the effort across timescales longer than any civilization has ever maintained. A specific technical program is uncertain. The same resources, invested differently, could make profound differences in the quality of life and the development of knowledge within the bounds of the home star system. Not failure, not giving up. A rational allocation of finite resources against infinite possibility made by beings who understood the numbers. And consider what the light speed limit means for communication alone, entirely separate from the travel problem. A civilization 1,000 light-years away that detects our earliest radio signals will not receive those signals until approximately the year 2900. If they respond immediately, their reply arrives here no earlier than the year 3900. A round-trip exchange takes a minimum of 2,000 years. 2,000 years, longer than the entire span of recorded Western civilization. For that exchange to occur, both civilizations must simultaneously maintain consistent intent, consistent technology, consistent organizational continuity, and consistent awareness that the exchange is happening for 2,000 years without interruption. 2,000 years during which no change of government, no scientific revolution, no economic collapse, no cultural transformation is severe enough to break the chain of attention and purpose required to sustain the exchange. We have no precedent for this. No human institution has maintained a specific narrow technical mission for 2,000 years. The longest institutional continuities in human history involve large, flexible organizations pursuing broad and general goals, not focused technical programs. The concept of a civilization sustaining a precisely defined communication project across a period longer than all of recorded history, with no response within any individual lifetime and no way to follow up within any generation, has no analogue in human experience. A civilization 5,000 light-years away requires a 10,000-year round trip. A civilization 50,000 light-years away requires a 100,000-year round trip. Longer than the existence of behaviourally modern Homo sapiens. Longer than the entire span of human civilization times 10. There is a specific quality to the silence of the sky that deserves to be named. We have been listening systematically since the 1960s. The SETI program, Search for Extraterrestrial Intelligence, has pointed radio telescopes at thousands of stars over more than 60 years. The most comprehensive surveys have covered a significant fraction of the observable sky across a wide range of frequencies. Modern instruments are sensitive enough to detect artificial signals comparable to what our own civilization produces, from distances of tens of light-years. We have detected no signal that requires intelligence as its explanation. We have continued to find new worlds. Planet-hunting satellites and ground-based telescopes have now confirmed the existence of thousands of exoplanets, with estimates suggesting that the average star in the galaxy has roughly one planet orbiting it. Many of those planets orbit in the habitable zone of their parent star, the range of distances where liquid water can exist on a surface. The number of potentially habitable worlds in the Milky Way alone is estimated in the billions. Billions of potentially habitable worlds. 60-plus years of systematic listening. Nothing. The silence is not ambiguous. It is not the silence of a search that has not yet reached far enough. It is the silence of a universe that, within the distances and timescales we can currently search, appears to contain no other technological civilization in the process of broadcasting. That could mean no one is there. It could mean everyone is hiding. It could mean everyone is listening but no one is transmitting first, a civilizational prisoner's dilemma played out across the galaxy. It could mean the wall stopped everyone before they reached the stage of broadcasting across interstellar distances in the first place. Each of these explanations has a different emotional weight. The first is lonely but simple. The last is complicated in a way that changes how we think about what we're doing when we look up. Every civilization in the galaxy faces this arithmetic. The light speed limit that prevents ships from reaching between stars also prevents communication on timescales that any individual or institution can hold in attention. The universe is not structured to make contact easy. It is structured to make it systematically, relentlessly difficult. And the difficulty grows with distance in a way that no technology currently imagined can overcome. Maybe intelligence appears regularly in the galaxy. Maybe it looks outward. Maybe it finds the wall. Maybe it understands the wall precisely enough to know that the universe drew this boundary around everyone equally. And maybe, in understanding that, it makes a peace with the silence that we have not yet had to make. The galaxy may be full of civilizations that looked at the same numbers we are looking at and reached the same conclusions. Each one isolated not by emptiness but by geometry. Separated not by absence, but by the structure of the space-time they all inhabit and share and cannot, except in the most extravagant expenditure of resources, cross. The silence may not be empty. It may be the sound of everyone who looked up, understood, and decided to build something beautiful where they were. And it may be separated from us not by emptiness, but by exactly the same wall we are looking at right now. And yet the story does not end there. Because there is one kind of mission that does not need to solve all of those problems simultaneously. A mission that does not require exotic matter, or the resolution of causality paradoxes, or a crew willing to leave their own timeline. A mission that does not need to bring anyone home, that does not require the civilizational patience of a 46-year radio silence, that does not demand multi-generational institutional commitment, a mission small enough to escape the worst of the rocket equation, fast enough to arrive within a human generation, and practical enough that serious engineers are actively developing it right now. The most realistic version of our first step toward another star may not look like a starship. It may look like a postage stamp. That is close to literally true. Breakthrough Starshot is a program announced at a press conference in New York in April 2016. It was backed by the late Stephen Hawking, the theoretical physicist and cosmologist who spent his career exploring the mathematics of black holes and the early universe, and who had thought about the limits of human reach into space for decades, and Yuri Milner, a Russian-Israeli entrepreneur who has made substantial investments in fundamental science research through the Breakthrough Prize Foundation. Following the announcement, a serious technical team was assembled, drawing physicists and engineers and materials scientists from universities and research laboratories at multiple institutions. The proposal is to send a fleet of spacecraft to the Alpha Centauri system, not in 73,000 years, not in 42 years, in roughly 20 years of travel time. Each spacecraft in the fleet is a chip, approximately 1 centimeter across, weighing a fraction of a gram, carrying miniaturized cameras, sensors, communication electronics, and a power source. Each chip is attached to a light sail, a thin reflective membrane perhaps a few meters across and weighing another fraction of a gram. Total mass of the complete spacecraft, chip plus sail, approximately 1 gram. 1 gram. The mass of a paperclip. The mass of a large postage stamp. The propulsion method does not involve any fuel aboard the spacecraft. It does not involve any engine or thruster or propellant of any kind. It exploits a physical phenomenon that has been known for over a century and measured precisely in the laboratory. Light carries momentum. When a photon of light reflects off a surface, it transfers a small but real amount of momentum to that surface. This is radiation pressure. It is why comet tails always point away from the sun regardless of which direction the comet is travelling. It is why solar sails proposed for decades are now actually being tested in space by organisations like the Planetary Society. Under ordinary conditions, with ordinary light sources, radiation pressure is negligible. The sun's radiation pressure at Earth's distance produces a force of about 9 millionths of a Newton per square metre of sail, useless for any practical propulsion purpose. But a sufficiently powerful laser, tightly focused on a sufficiently light and reflective sail, can produce extraordinary acceleration. If the laser power is high enough, and the sail mass is low enough, and the reflectivity is high enough, the photon pressure can accelerate the sail to a significant fraction of the speed of light within a reasonable acceleration time. Breakthrough Starshot's design calls for a ground-based laser array covering roughly 1 square kilometre. Thousands of individual laser emitters, each phase-locked to all the others through sophisticated adaptive optics and signal processing, acting in synchrony as a single coherent beam, total combined power approximately 100 gigawatts. Roughly equivalent to the total electrical generating capacity of a large nation, focused into a single beam aimed at a sail the size of a dining table. The laser fires at each sail for roughly 10 minutes. During those 10 minutes, the photon pressure of 100 gigawatts of coherent laser energy accelerates the gram-scale spacecraft from rest to approximately 20% of the speed of light, about 37,000 miles per second, 1/5 of the maximum speed the universe allows. At 20% of light speed, Alpha Centauri is about 20 to 22 years away, depending on the precise target within the triple star system. A signal from the spacecraft transmitted at light speed after arrival reaches Earth approximately 4.3 years later. Total elapsed time from launch to first data from another stellar system, roughly 24 to 25 years. A person who is 30 years old at launch could be 55 when the data arrives. Old enough to have devoted their entire career to the project, young enough to still be active and present when the images and measurements come back. This is a human timescale, a single career, a single generation. Not 73,000 years. Not a multi-generational commitment requiring civilizational patience we have never demonstrated. One career. The engineering challenges are specific and real. The sail material challenge is probably the most fundamental. The sail must reflect essentially all of the incident 100 gigawatt laser energy, because even a tiny absorbed fraction of that power represents enormous heat. A sail that absorbs only 1/millionth of the incident beam is still absorbing 100 kilowatts per square meter, enough to heat and potentially ablate most materials within seconds. The sail must also be structurally stable at the nanometer scale thicknesses required to achieve gram-scale mass for a few meter sail. And it must maintain all of these properties throughout the 10-minute acceleration phase, including the phase when it is moving at an increasing fraction of light speed, and the laser light it is reflecting is Doppler shifted in frequency. No material currently exists that meets all these requirements simultaneously. The research programs working on this problem are investigating new metamaterials, photonic crystal structures, and composite layered designs. It is a genuine, unsolved materials science problem. But it is a materials science problem, not a physics problem. Materials science problems respond to research investment in ways that physics prohibitions do not. The pointing challenge involves maintaining the kilometer-scale laser array aimed precisely at a target the size of a dining table, while that target is accelerating away at increasing velocity, while the atmosphere above the array is introducing continuous small distortions into the beam. Adaptive optics can compensate for much of the atmospheric distortion. The required pointing precision, however, is significantly beyond what current adaptive optics systems achieve. The path forward involves higher speed wavefront sensors and deformable mirrors, combined with sighting the array at high altitude to reduce the column of turbulent atmosphere the beam must traverse. It is an engineering gap with a clear direction of improvement. The trajectory challenge involves launching the sail on a course so precisely aimed that after 4.24 light-years of unguided flight, the probe arrives within sensor range of the target. Any small error in the initial direction compounds over the crossing into a potentially large position error at arrival. The probe cannot correct its own trajectory. It must be aimed correctly once, at the beginning. This requires precise knowledge of Alpha Centauri's position and its proper motion across the sky over the 20-year crossing, combined with precise control of the beam direction during the acceleration phase. Solvable. Better astrometric data on the target system helps. Better beam control during the burn helps. Both are achievable. The communication challenge involves receiving a meaningful signal from a chip with a milliwatt transmitter and a centimeter-scale antenna at a distance of 4.24 light-years. The received signal will be extraordinarily faint. Detecting it requires antenna arrays larger and more sensitive than anything currently operating. Building such arrays is expensive and complex, but the physics is well understood. The challenge is engineering and cost, not physics. None of these challenges involve physics prohibitions. Each one is an engineering gap with a defined boundary and a known direction of improvement. They all respond to investment. Physics prohibitions do not. Beyond the immediate mission, some researchers see a longer arc in these ideas. Self-replicating probes, machines that can reproduce themselves using materials found at the destination, then depart for the next target. The concept was first analysed formally by mathematician John von Neumann. A fleet of self-replicating probes launched from Earth could, in principle, spread from star to star, each probe producing multiple copies at each destination, the total number growing exponentially, the expansion front sweeping outward at some fraction of light speed. In a galaxy 100,000 light-years across, even at modest travel speeds, a self-replicating expansion would saturate the galaxy in tens of millions of years. This is one framing of why the Fermi paradox is so quiet. If any civilization in the galaxy's history had done this, we should see evidence of it everywhere. We see none. Its absence says something. But the concept itself points toward a model of interstellar presence quite different from the crude starship. Not one ship carrying a crew across the dark. Many small machines, each carrying only the minimum, each reaching a destination, and doing some useful work and sending data home and perhaps producing more machines. Not exploration as voyage. Exploration as process. Slow, patient, expanding. And beyond machines, there is information. If the goal is not to send biological matter through space but to transmit the patterns that constitute minds, then light speed is less of a barrier than it first appears. A complete human genome is a few gigabytes of data. A sufficiently detailed description of a human brain's connectivity, including the synaptic weights and molecular architecture that carry memory and personality and learned capability, is a much larger data set but finite. It can in principle be encoded and transmitted as a radio or laser signal. That signal travels at the speed of light. Across 4.24 light-years, it takes 4.24 years to arrive. Not 25 years, not 42 years, 4.24 years. At the destination, if a receiving system exists, placed there by prior physical probes over the preceding decades, the information could in principle be used to reconstruct biological organisms using local materials or to instantiate the patterns of those minds in synthetic substrates. The result would carry the memories, skills, personality, and knowledge of the civilization that sent the signal. Whether such a reconstruction is the same person, or a continuation of them, or a copy, or something philosophically distinct, is a question that the philosophy of personal identity has not yet resolved. Whether the same pattern instantiated in different substrate constitutes personal continuity is a question that may not have a single correct answer, independent of our decisions about what we mean by personal identity. But as a strategy for extending the presence and knowledge of a civilization across interstellar distances, information first transmission has a cold elegance. The signal travels at the maximum speed the universe permits. It carries no mass. It incurs no radiation dose. It experiences no time dilation. The problem shifts from how do we move bodies through space faster than physics allows to what is worth sending, and how do we ensure it can be received and used when it arrives. Sometimes the future does not arrive as a leap. Sometimes it arrives as a signal sent by something small and precise, moving through the dark at the only speed the universe reliably allows. There is one more thing worth saying about the physics of the warp drive, and it concerns the relationship between the mathematics and the experimental program. In physics, the path from a valid mathematical solution to an experimental test is not always obvious. General relativity predicted black holes mathematically in 1916. The first strong observational evidence for their existence did not arrive until the 1970s, and the first direct image of a black hole's shadow was not produced until 2019. More than a century passed between the mathematical prediction and the visual confirmation. During most of that time, many physicists remained uncertain whether black holes were genuine physical objects or merely mathematical artifacts of the theory, singularities that the universe would somehow prevent from actually forming. The Alcubierre metric is in a somewhat similar position. It is a valid mathematical solution that has existed for 30 years. It has never been tested experimentally in any form. The question of whether it describes something the universe actually permits, at any scale, remains open. The program to answer that question at microscopic scales, pursued by researchers at Applied Physics and associated groups, represents the first serious experimental program directed at the warp drive question since Alcubierre published. If they succeed in creating a detectable microscale spacetime distortion consistent with warp-like geometry, the result would not be a starship. It would be a measurement, a confirmation that the geometry is physically realizable, not merely mathematically permissible. The difference between a physics paper and a physics experiment. History suggests that physics experiments have a way of leading places their designers did not expect. The first tests of electromagnetic induction were demonstrations of a laboratory curiosity. The first nuclear fission experiments were measurements of cross-sections and binding energies. The first semiconductor experiments were studies of the electrical properties of germanium. None of the researchers performing those experiments knew they were beginning technologies that would reshape human civilization. They were simply trying to learn whether the mathematics corresponded to reality. The warp drive experiments being proposed now are at a similar stage. Small, underfunded compared to the scale of the question, uncertain in their outcomes, but aimed at the right question. Does the geometry correspond to anything real? If the answer is yes, even at scales too small to be useful, the next question becomes how to make it larger. And that question has always been an engineering question. And engineering questions, unlike physics questions, respond to money and attention and time. We are not close to a warp drive. We may never be close to a warp drive. The obstacles are real, and several of them may prove insurmountable. But for the first time in the 30 years since Alcubierre published, the question of whether the drive is physically realizable is becoming experimentally approachable rather than merely theoretically debatable. And that transition, from thought experiment to laboratory program, is the same transition that has marked the beginning of every technology that now seems obvious and inevitable in retrospect. What we do not yet know is whether this transition marks the beginning of a technology or the beginning of a very precise understanding of why the technology cannot be built. Both outcomes are worth having. The precise understanding of why the warp drive cannot be built, if that turns out to be the answer, would be one of the deepest things we have ever learned about the structure of the universe. It would tell us that the geometry of reality is sealed at a level below what we currently understand, that the mathematics permits what the physics forbids, and that the prohibition is operating through a mechanism we have not yet identified. That would not be a failure. That would be a discovery. One that would reframe every subsequent conversation about interstellar travel, about the Fermi paradox, about the nature of the universe and our place within it. A discovery that would mean the wall is absolute, and that every civilization in the history of the galaxy has looked at the same wall, measured it, understood it, and made their peace with it. Or the answer is different. The geometry is realizable. The obstacles are engineering problems. The universe, strange and permissive in ways we have not yet fully mapped, contains a door. Either way, we are close to knowing which kind of universe we live in. And that knowledge, whatever it turns out to be, is the most important navigation fix we could ask for. And this brings us to something that rarely gets discussed in conversations about faster-than-light travel, which is what we would do with it if we had it. The immediate answer is obvious. We would go to the nearest stars, we would look for planets, we would look for life. We would look for any trace of intelligence, whether it is still present or long extinct, whether it left behind ruins or signals or artifacts, or simply the chemical signature of biology on a world that was once inhabited. We would answer the question that has been asked since the first human being looked up at the night sky and wondered whether they were alone. That answer matters in itself. It may be the most important single answer in human history. Whether the universe contains other intelligence, whether we are alone or accompanied, shapes everything from our philosophical self-understanding to our practical sense of what is possible for the long-term future of mind in the cosmos. Knowing the answer, either answer, would be transformative in a way that is difficult to fully anticipate, but there is a longer arc to consider. If faster-than-light travel existed, and if the galaxy turned out to contain life but no other civilizations currently broadcasting, then the question of what we do with interstellar access becomes one of the most consequential choices in human history. The galaxy has 400 billion stars. Many of them have habitable planets. The vast majority of those planets are currently uninhabited by technological civilizations. They are available in a sense for whatever use intelligence might make of them. That is not a resource to be exploited in the extractive sense. It is a kind of possibility space, the possibility of civilizations on other worlds, of ecosystems elsewhere, of whatever intelligence might eventually arise there if left undisturbed for another billion years. The presence of that possibility space changes the scale of what is at stake in every decision a civilization makes about itself. A civilization capable of interstellar travel is not merely a civilization that can go places. It is a civilization whose choices have consequences at a galactic scale. We are not that civilization yet. We may not become it within any timescale that any person alive today will personally experience. But the physics is the physics. If the warp drive is possible, if the wall has a door, then the question of what to do with it is the question that follows. And that question is not a physics question. It is a civilizational question. A question about what kind of intelligence we want to be. There is a reason the Fermi paradox feels more urgent the more carefully you study it. It is not just a puzzle about where everyone else is. It is a question directed at us, about what we would do with the capability if we had it. Whether we would be the kind of civilization that used it carefully and responsibly, or the kind that did not. The silence of the galaxy is not only information about others, it may be a mirror, and perhaps the most honest response to that mirror is this. We do not yet know which kind of civilization we are. We have not had to decide. The decision has been deferred by the physics, which has kept interstellar travel just beyond our reach for the entire duration of our technological civilization. But the physics is being mapped with increasing precision. The wall is being measured from up close for the first time, and eventually the question of what to do if the wall has a door will stop being hypothetical. When that day comes, we will need to be ready to answer it. One more thing deserves to be said about the scale of what we are attempting, and about what the attempt itself means. The history of science is a history of questions that seem too large to answer. The composition of the stars seemed unknowable before spectroscopy. The age of the Earth seemed unmeasurable before radiometric dating. The existence of other galaxies beyond our own was considered uncertain as recently as 1920. The structure of DNA was unknown in 1950. The existence of exoplanets was unconfirmed until 1992. In each case, the question seemed too far beyond our reach to take seriously as an engineering target. In each case, the tools to approach it were developed not because anyone set out to answer that specific question, but because the incremental progress of science and technology eventually created the conditions in which the question became answerable. Faster-than-light travel may follow the same arc, or it may not. The distinction between a physics question that yields to enough cleverness and investment and a physics prohibition that is genuinely and permanently inscribed in the structure of reality is not always obvious from the inside of the puzzle. We have been wrong before about which kind of question we are facing, usually in the direction of assuming a question was harder than it was. What we can say with confidence is this: the question is real, it is being taken seriously, it is being approached with better mathematical tools and better experimental programs than at any prior point, and the answer, when it comes, will matter. So, Have we found a real way to travel faster than light? Not yet, but not never, and the distance between those two positions has measurably shifted in the last 30 years, in ways that matter even if they fall far short of a working design. The warp drive is real mathematics. The Alcubierre metric is not a science fiction device. It is a genuine, valid solution to Einstein's field equations. The same equations that correctly predicted gravitational waves before any detector capable of measuring them existed. The same equations that require clock corrections in every GPS satellite. Because time runs faster at orbital altitude than on the ground, corrections applied in every GPS calculation on every phone in the world, every day. These equations have been tested against physical reality more precisely than almost any other theory in the history of science. And they permit a geometry of space-time that would, if physically realized, allow crossing interstellar distances in a time with no obvious lower bound. The exotic matter problem is real, though its magnitude appears to depend on design choices and may be reducible by geometries not yet fully explored. The vacuum radiation problem is real, and the implications for anything at the destination are serious. The causality paradoxes at true superluminal speeds are real and unresolved. The navigational isolation inside the bubble is real and unaddressed, but the character of these problems has changed. They are no longer simply reasons why the warp drive is impossible. They are specific, identifiable obstacles with definable boundaries, against which specific research programs are making specific progress. The problem has moved from categorically prohibited to specifically obstructed. Specific obstacles can be targeted. Categorical prohibitions cannot. There is something in this story that runs deeper than propulsion physics. Faster-than-light travel is the specific dream that the universe refuses to make easy. Not just expensive, not just difficult. Structurally resistant in a way that runs through the foundations of physical reality. Every approach reveals a different obstacle. Every proposed solution opens onto a different problem. The wall does not have one face. It has many, and each reflects a different deep feature of the structure of space-time and causality and the quantum vacuum. Every other capability we have ever pursued as a civilization has followed a recognizable pattern. Someone imagines it. Someone crude builds a first version. Successive generations refine it. The imagined capability becomes ordinary technology. Flight followed this arc over roughly 60 years. Nuclear energy followed it. Computing followed it. Genetic engineering is following it now. At every stage, serious people said the thing was impossible. At every stage, they were eventually wrong. Faster-than-light travel may be different in kind, not just harder, geometrically constrained, written into the structure of reality at a level that persists regardless of engineering ingenuity or energy scale or material sophistication. Or it may not be different, because every step toward the theoretical viability of the warp drive has been a discovery that the universe is stranger and more permissive than the previous map suggested. We did not know space-time could curve until 1905. We did not know that curvature could geometrically describe gravity until 1915. We did not know the quantum vacuum had measurable structure until the Casimir effect was confirmed in the 1950s. We did not know that positive energy soliton geometries might support warp-like effects without requiring exotic matter until 2021. Every step revealed a universe that the previous generation's understanding had been too small to contain. There is no guarantee that the next step will not reduce the energy requirement to something on an accessible engineering spectrum. No guarantee that the step after that will not reveal how the causality paradox can be navigated in a specific class of physically realizable geometries. No guarantee that a physicist working 50 years from now, in a laboratory that does not yet exist with mathematical tools not yet developed, will not publish something that changes the shape of this problem the way each previous discovery changed it. The history of physics is, in a profound sense, the history of maps that turned out to be too small. The wall may be exactly where it appears. Absolute. Uncrossable. A true geometric feature of reality that no amount of cleverness or energy or engineering can root around. The universe may have drawn this line in permanent ink, or the wall may be, as it has been every time before, the edge of an incomplete map. We do not know which. We know only where we have looked so far. Faster-than-light travel teaches us something uncomfortable about the universe. It is not designed around human urgency. The nearest star does not move closer because we want it to. Light does not speed up because the distances feel unfair. Space does not soften because the mission matters to us. The equations do not simplify out of consideration for our longing. The universe was not constructed to be convenient for the species that eventually developed the curiosity to ask these questions. And still, we keep measuring. We keep running the calculations, finding new geometries and new constraints and new possibilities nested inside old impossibilities. We keep sending things outward, one careful step further than the last. Voyager 1, still transmitting from beyond 23 billion miles, the farthest any human artifact has ever been, instruments designed in the 1970s still returning data from the boundary of interstellar space. New horizons, past Pluto, moving outward through the Kuiper belt toward the same medium Voyager now crosses. And someday, perhaps within the lifetimes of people working in physics laboratories right now, a gram-scale sail riding a focused beam of light across 25 trillion miles of dark to transmit back, in a signal that takes 4.3 years to arrive, the first image ever captured from within another solar system. That image will be blurry. It will carry less information than a photograph taken on an ordinary phone. It will arrive long after the people who decided to try had time to wonder whether they would live to see it, and it will be the most important image in the history of human civilization. Not because of what it shows, because of what it proves, that the universe is not sealed, that the wall has at least one door, that the silence between stars is not the permanent condition, that the first step across 4.24 light-years is possible with technology that exists in concept now and could exist in practice within a single generation. The first step does not solve the problem of the stars. It does not bring Proxima Centauri close, or make the galaxy navigable, or resolve the warp drive equations, or answer the Fermi paradox. It is 1 gram of metal and circuitry moving through the dark at 20% of light speed, carrying a camera the size of a fingernail, but it changes what we know about what is possible. And changing what we know about what is possible is how every journey in the history of exploration has ever actually begun. Maybe faster-than-light travel is not, in the end, proof that the stars are within reach. Maybe it is proof that we have finally begun to understand the exact size and shape of the reach itself, and that understanding, precise and uncomfortable and vast and still incomplete, is the first honest step toward everything that comes after it. But there is something we have not yet examined in this conversation, something that sits quietly at the center of the faster-than-light question and rarely receives the attention it deserves. Not the mechanics of the warp drive, not the rocket equation, or the time dilation, or the silence of the Fermi paradox, something simpler and more personal, the destination. We have been talking about Proxima Centauri as though it were a coordinate, a number, the nearest data point in a catalogue of unreachable places. But Proxima Centauri is not just a star on a list. It is a specific place, a place about which we now know something remarkable. In 2016, astronomers using the High Accuracy Radial Velocity Planet Searcher instrument at the European Southern Observatory in Chile confirmed the existence of a planet orbiting in the habitable zone of Proxima Centauri. The planet is called Proxima b. It orbits its star at a distance of about 7.5 million kilometers, much closer than Earth orbits the Sun, but close enough that Proxima b sits in the zone where liquid water could exist on a rocky surface. Proxima Centauri is a red dwarf star, much smaller and cooler than our Sun, so the habitable zone is far closer in. Proxima b has a minimum mass of about 1.07 Earth masses. It is almost certainly a rocky planet. It completes a full orbit of its star in 11.2 days, and it sits 4.24 light-years from Earth, the nearest star to the nearest possible rocky world in its habitable zone. Now, we do not know whether Proxima b has an atmosphere. We do not know whether it has liquid water. We do not know whether it is bombarded by the intense stellar flares that red dwarf stars produce, which could strip an atmosphere away and sterilize a surface, or whether it has a strong enough magnetic field to deflect those flares. We do not know whether it's tidally locked to its star, showing the same face perpetually toward the light and leaving one hemisphere in permanent darkness. We do not know whether it is habitable. We do not know whether it is inhabited. We know it exists. We know its approximate mass. We know its orbital period. We know it is in the right place. And we know that it is 4.24 light-years away. The gap between what we know and what we want to know about that world is at present unbridgeable by any instrument on Earth or in Earth orbit. The angular separation between Proxima b and its star is so small, and the star so much brighter than any reflected light from the planet, that directly imaging the planet and analysing its atmosphere by conventional means is beyond our current capability. We can detect the planet's existence through its gravitational tug on the star. We cannot yet see it, but breakthrough starshot changes that calculation. A gram-scale probe reaching Proxima b at 20% of light speed could, on its flyby, capture images of the planet at resolutions impossible from Earth. It could measure the temperature of the surface, detect the composition of an atmosphere if one exists. Look for the specific chemical signatures: oxygen, methane, water vapour, the gases that in combination are difficult to explain without biology, that we call biosignatures. It could look for the signs of life, not with certainty. A brief flyby does not allow for the kind of sustained observation that a definitive answer would require. The images would be blurry by modern standards. The data would be limited. But it would be real data from the surface of a world orbiting another star. Real pixels, real temperatures, real atmospheric chemistry, or the confirmed absence of it. And that is a different category of knowledge from everything we currently have. The knowledge that a world 4.24 light-years away is dry and airless and lifeless would be one of the most important things we have ever learned. The knowledge that it has an atmosphere would be more important still, and the knowledge that its atmosphere contains the chemical signatures of biological processes would be the most important discovery in the history of science. More important, arguably, than anything else humanity has ever found out about anything. That answer is sitting out there, 4.24 light-years away. We cannot currently reach it. The instruments to obtain it do not yet exist in deployable form, but the physics of obtaining it is understood. The engineering roadmap is being developed. The timeline, while long, is measured in decades and not in centuries or millennia. This is what makes the interstellar problem urgent in a way that it was not, say, 50 years ago. We now know there is something there to learn. Not just a star. A world about which a specific answerable world-altering question can be asked. And the answer to that question will arrive only when something physical gets close enough to gather it. There is another solution to the faster-than-light problem that we have not yet discussed, and it deserves a mention even though its status is more ambiguous than the warp drive. Wormholes. The idea of a traversable wormhole, a shortcut through space-time that connects two distant regions through a tunnel shorter than the space between them, is older than the Alcubierre metric. The mathematical object underlying it, called an Einstein-Rosen bridge, was identified by Einstein and his collaborator Nathan Rosen in 1935, almost immediately after general relativity was completed. What Einstein and Rosen found was that the mathematics of a black hole, followed through to its logical conclusion, produced not just a region of infinite density at the singularity, but a tunnel in space-time connecting that singularity to a second region. A mirror image of the black hole on the other side. The Einstein-Rosen bridge is a wormhole, but it is not a traversable wormhole. It collapses too quickly for anything to pass through it. The tunnel forms and closes faster than light could traverse it. In the original formulation, the bridge is present but useless. In 1988, Kip Thorne, a physicist at Caltech, who would later share the Nobel Prize for his work on gravitational wave detection, and his colleagues Michael Morris and Ulvi Yurt-Siver, published an analysis asking whether a wormhole could be made traversable. The answer was yes, with a familiar condition. To hold the throat of the wormhole open long enough for anything to pass through it, the wormhole would need to be threaded with exotic matter with negative energy density. The same Casimir effect type of negative energy density required by the Alcubierre drive in enormous quantities, so the wormhole shares the fundamental obstacle with the warp drive. Both require exotic matter. Both require negative energy density at a scale that makes them, in current terms, physically unrealizable. And like the warp drive, the wormhole also raises causality questions. If a traversable wormhole were created, and one end were accelerated to high velocity and then returned, the two ends of the wormhole would be at different points in time due to the time dilation of the accelerated end. The result would be a wormhole that connects not just two places but two times. A time machine. The chronology protection conjecture, Stephen Hawking's proposed principle that the universe forbids closed time-like curves, would presumably apply to wormholes as well as warp drives. If the conjecture is true, something prevents traversable wormholes from forming just as surely as it prevents the causality paradoxes of superluminal travel. But there is something interesting that has emerged from the study of wormholes in the last decade or so, something that touches on a question much deeper than propulsion. a possible connection between wormholes and quantum mechanics that, if correct, would mean wormholes are not exotic additions to physics, but fundamental features of the universe at the quantum scale. In 2013, physicists Juan Maldacena and Leonard Susskind published a paper with a title so terse and unusual that it became famous as a shorthand in the field. The title was ER equals EPR. ER refers to Einstein-Rosen bridges, the wormhole. EPR refers to Einstein-Podolsky-Rosen, the famous 1935 paper that introduced quantum entanglement, named for its three authors. Maldacena and Susskind proposed that these two apparently unrelated phenomena, one from general relativity and one from quantum mechanics, might be the same thing, that the quantum entanglement between two particles might be, in a precise mathematical sense, a microscopic wormhole connecting them. If ER equals EPR, if entanglement and wormholes are dual descriptions of the same underlying physics, then wormholes are not rare and exotic features of spacetime that require special conditions to create. They are ubiquitous. Every pair of entangled particles in the universe is connected by a microscopic wormhole. The quantum vacuum itself is a foam of microscopic wormholes, far too small to be traversed by anything, but present everywhere. This idea is speculative, it is beautiful, and it connects two of the deepest unsolved problems in physics, the reconciliation of general relativity with quantum mechanics, in a way that has attracted serious attention from some of the most capable, theoretical physicists currently working. Whether it is correct, and what it would mean for practical traversable wormholes if it is, remains entirely unknown. But it suggests something worth holding on to, that the geometry of spacetime and the structure of quantum entanglement may be more deeply connected than anyone imagined when these theories were first developed, and that a complete understanding of the connection between them might reveal new possibilities or new absolute prohibitions that neither theory alone could show. There is one more feature of the faster-than-light problem that deserves attention, and it is the one that makes the problem urgent on a timescale much longer than any human lifetime. The universe is expanding. Not just expanding, but accelerating in its expansion. The space between galaxy clusters is growing faster over time, not slower. This was discovered in 1998 by two teams of astronomers studying distant supernovae, and was awarded the Nobel Prize in Physics in 2011. The expansion is driven by something called dark energy, a property of space itself that causes it to expand as the universe ages. Its ultimate nature is unknown. The consequence of this expansion for interstellar and intergalactic travel is profound. Currently, the observable universe extends roughly 46 billion light-years in every direction, and contains somewhere around 2 trillion galaxies. Most of those galaxies are already receding from us faster than light due to the expansion of space, but they are still within our observable universe because the light they emitted long ago, when they were closer, is only now reaching us. We can see them, we cannot currently reach them, but the expansion means that over time those distant galaxies will recede faster and faster. The light they emit now will never reach us, because the space between us and them is expanding faster than light can cross it. Eventually those galaxies will pass beyond what physicists call the cosmic event horizon, the distance beyond which the expansion carries things away faster than light can chase them. Once a galaxy crosses our cosmic event horizon, it is gone. Not destroyed, not gone from the universe, gone from our universe, permanently unreachable, permanently unobservable. Every year, more galaxies cross that horizon and are lost to us forever. In roughly 2 trillion years, the Milky Way and its local group of about 50 nearby galaxies will be the only structures remaining within our observable, reachable universe. Everything else will have receded beyond the horizon. The night sky will be dark. The rest of the universe will be inaccessible, not just practically but in principle. The cosmic event horizon will have swallowed everything except our immediate gravitational neighborhood. From a civilizational perspective, this is not an urgent crisis. 2 trillion years is not a planning horizon that makes sense for any human institution, but it is relevant to how we think about the long-term importance of interstellar and intergalactic travel. The window for reaching the broader universe is not infinite. It is closing, slowly, imperceptibly slowly by any human timescale, but closing. And within our own galaxy, the same logic applies on a smaller scale. The stars of the Milky Way will not burn forever. The Sun will exhaust its hydrogen fuel in roughly another 5 billion years. Other stars have shorter or longer lifetimes depending on their mass. The most massive stars burn out in millions of years. The smallest red dwarfs, stars like Proxima Centauri, can burn for trillions of years. But eventually all stars die, the galaxy will darken, the habitable window in the universe is finite. This does not make faster-than-light travel urgent in any practical sense. It makes it meaningful in a deeper sense. The question of whether intelligence can eventually spread beyond the world where it first arose is not only a question about exploration and curiosity, it is a question about the long-term survival of everything that intelligence has ever produced and might yet produce. Music, mathematics, memory, the knowledge that the universe contains certain patterns and structures and histories, the continuity of something that has awareness of itself and the world it inhabits. Whether any of that survives the death of its home star is entirely a function of whether intelligence can, in principle, cross the spaces between stars. And that question comes back, as it always does, to the speed of light. The wall that prevents us from reaching Proxima Centauri in a human lifetime is the same wall that, over timescales measured in billions of years, limits the reach of any intelligence arising on any world in any galaxy. The local problem and the cosmic problem are the same problem wearing different timescales. This is perhaps the deepest reason to care about faster-than-light travel. Not because any of us will live to see it achieved, not because the stars are calling to us in any way we can currently answer, but because the question of whether the wall is absolute, whether it applies equally at all timescales, whether it is the final word on how far awareness can travel in this universe, is one of the most fundamental questions we can ask about the long-term nature and possibilities of mind. We are early, we are small. We are on one rocky world around one ordinary star in one of 400 billion stars in one of 2 trillion galaxies. We have been technologically capable for a few hundred years at most. We have been asking the question of how to reach other stars for perhaps a century. By any cosmic measure, we have barely started. But we have started. The equations are on paper. The experiments are being designed. The sails are being fabricated in laboratories. The lasers are being planned. The mathematics of space-time geometry is being worked through more carefully than at any previous moment in history. The question of whether the wall has a door is being approached from more directions simultaneously than it ever has been. And somewhere in all of that work, patient and incremental and uncertain as it is, the shape of the answer is slowly becoming clearer. So, have we found a real way to travel faster than light? Not yet, but not never. And the distance between those two positions has measurably shifted in the last 30 years, in ways that matter even if they fall far short of a working design. The warp drive is real mathematics. The Alcubierre metric is not a science fiction device. It is a genuine, valid solution to Einstein's field equations. The same equations that correctly predicted gravitational waves before any detector capable of measuring them existed. The same equations that require clock corrections in every GPS satellite, because time runs faster at orbital altitude than on the ground. Corrections applied in every GPS calculation on every phone in the world, every day. These equations have been tested against physical reality more precisely than almost any other theory in the history of science. And they permit a geometry of space-time that would, if physically realized, allow crossing interstellar distances in a time with no obvious lower bound. The exotic matter problem is real, though its magnitude appears to depend on design choices and may be reducible by geometries not yet fully explored. The vacuum radiation problem is real, and the implications for anything at the destination are serious. The causality paradoxes at true superluminal speeds are real and unresolved. The navigational isolation inside the bubble is real and unaddressed, but the character of these problems has changed. They are no longer simply reasons why the warp drive is impossible. They are specific identifiable obstacles with definable boundaries, against which specific research programs are making specific progress. The problem has moved from categorically prohibited to specifically obstructed. Specific obstacles can be targeted. Categorical prohibitions cannot. There is something in this story that runs deeper than propulsion physics. Faster-than-light travel is the specific dream that the universe refuses to make easy. Not just expensive, not just difficult. Structurally resistant in a way that runs through the foundations of physical reality. Every approach reveals a different obstacle. Every proposed solution opens onto a different problem. The wall does not have one face. It has many, and each reflects a different deep feature of the structure of space-time and causality and the quantum vacuum. Every other capability we have ever pursued as a civilization has followed a recognizable pattern. Someone imagines it, someone crude builds a first version, successive generations refine it, the imagined capability becomes ordinary technology. Flight followed this arc over roughly 60 years. Nuclear energy followed it. Computing followed it. Genetic engineering is following it now. At every stage, serious people said the thing was impossible. At every stage, they were eventually wrong. Faster-than-light travel may be different in kind, not just harder, geometrically constrained. Written into the structure of reality at a level that persists regardless of engineering ingenuity or energy scale or material sophistication. Or it may not be different, because every step toward the theoretical viability of the warp drive has been a discovery that the universe is stranger and more permissive than the previous map suggested. We did not know space-time could curve until 1905. We did not know that curvature could geometrically describe gravity until 1915. We did not know the quantum vacuum had measurable structure until the Casimir effect was confirmed in the 1950s. We did not know that positive energy soliton geometries might support warp-like effects without requiring exotic matter until 2021. Every step revealed a universe that the previous generation's understanding had been too small to contain. There is no guarantee that the next step will not reduce the energy requirement to something on an accessible engineering spectrum. No guarantee that the step after that will not reveal how the causality paradox can be navigated in a specific class of physically realizable geometries. No guarantee that a physicist working 50 years from now, in a laboratory that does not yet exist, with mathematical tools not yet developed, will not publish something that changes the shape of this problem the way each previous discovery changed it. The history of physics is, in a profound sense, the history of maps that turned out to be too small. The wall may be exactly where it appears, absolute, uncrossable, a true geometric feature of reality that no amount of cleverness or energy or engineering can root around. The universe may have drawn this line in permanent ink, or the wall may be, as it has been every time before, the edge of an incomplete map. We do not know which. We know only where we have looked so far. Faster-than-light travel teaches us something uncomfortable about the universe. It is not designed around human urgency. The nearest star does not move closer because we want it to. Light does not speed up because the distances feel unfair. Space does not soften because the mission matters to us. The equations do not simplify out of consideration for our longing. The universe was not constructed to be convenient for the species that eventually developed the curiosity to ask these questions. And still, we keep measuring. We keep running the calculations, finding new geometries and new constraints and new possibilities nested inside old impossibilities. We keep sending things outward, one careful step further than the last. Voyager 1, still transmitting from beyond 23 billion miles, the farthest any human artifact has ever been, instruments designed in the 1970s still returning data from the boundary of interstellar space. New horizons, past Pluto, moving outward through the Kuiper belt toward the same medium Voyager now crosses. And someday, perhaps within the lifetimes of people working in physics laboratories right now, a gram-scale sail riding a focused beam of light across 25 trillion miles of dark to transmit back, in a signal that takes 4.3 years to arrive, the first image ever captured from within another solar system. That image will be blurry. It will carry less information than a photograph taken on an ordinary phone. It will arrive long after the people who decided to try had time to wonder whether they would live to see it. And it will be the most important image in the history of human civilization, not because of what it shows, because of what it proves, that the universe is not sealed, that the wall has at least one door, that the silence between stars is not the permanent condition, that the first step across 4.24 light-years is possible with technology that exists in concept now and could exist in practice within a single generation. The first step does not solve the problem of the stars. It does not bring Proxima Centauri close, or make the galaxy navigable, or resolve the warp drive equations or answer the Fermi paradox. It is 1 gram of metal and circuitry moving through the dark at 20% of light speed, carrying a camera the size of a fingernail. But it changes what we know about what is possible. And changing what we know about what is possible is how every journey in the history of exploration has ever actually begun. Maybe faster-than-light travel is not in the end proof that the stars are within reach. maybe it is proof that we have finally begun to understand the exact size and shape of the reach itself. And that understanding, precise and uncomfortable and vast and still incomplete, is the first honest step toward everything that comes after it. Strap in, keep looking outward, and stay with the crew. If you want more mission briefings like this, subscribe for the next journey.